Dear ladies and gentlemen, let me welcome you to EAI MobiQuitous 2020 conference held in this virtual interactive setting. I am Karolina Marcinova and I would like to address all of you on behalf of EAI and MobiQuitous 2020. Unfortunately, I am not able to meet all of you in person, so I'm using this opportunity to address the organizing committee, the keynote speakers, the authors, and all the participants on behalf of EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the whole organizing committee for their hard and excellent work throughout the whole process of the conference preparation. Lastly, let me use this message to invite you to join us again at EAI MobiQuitous 2021, which will take place in Beppu, Japan in November. Should you be interested in becoming a part of next year's organizing committee or technical program committee, please do not hesitate to contact me at my email address below. Similarly, if you are interested in discussing other possible cooperation, a conference, a workshop, or a new event altogether, please contact me at my email address as well. Now, my colleague Michal will present you with what EAI does, who we are, and how you can get involved in our various activities. Thank you for your attention and enjoy EAI MobiQuitous 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello, my name is Antonio Teófilo. I will present RedMesh, a Wi-Fi-Direct network formation algorithm. This is a joint work with João Lourenço and Hervé Paulino. We are affiliated in Nova Links Laboratory from Nova University of Lisbon and also in ISEL, both from Portugal. We will start with the context and our motivation. We will use this scenario, where points are devices. The scenario does not have the support of a communication infrastructure, but nowadays mobile devices have device-to-device communication capabilities. The question is then, can we achieve communication between all nodes using device-to-device communication? To achieve communication between all nodes, we will use Wi-Fi-Direct. We can see that Wi-Fi range is enough to provide connection. The Wi-Fi radio visibility network confirms that all nodes can be connected. With Wi-Fi Direct, we can form groups, but Wi-Fi Direct groups do not provide connectivity between all nodes. And Wi-Fi Direct specification does not provide intergroup communication. So communication cannot be achieved, but there are some solutions. Now we will present some background concepts and discuss the state-of-the-art in Wi-Fi Direct network formation algorithms. Let's start with some background about Wi-Fi Direct. Wi-Fi Direct enables to form groups. Groups are managed by one central node called Group Owner, or GO for short. Groups can have up to 8 clients, and the specification does not provide intergroup communication. However, there are some solutions to cross Wi-Fi Direct groups. We will use connection and communication topologies for direct and indirect connections between group owners. To connect group owners directly and form 3 networks, we use the GO-GO topology. This topology requires one message to cross one group, and group owners must have their Wi-Fi interface connected. This topology allows the use of unicasts. To connect group owners indirectly and form mesh networks, we use the GO-CR-GO topology. This topology connects two group owners using one relay client in between. It requires two messages to cross one group and allows the use of unicasts. Here you will see the existing Wi-Fi-Direct network formation algorithms. Baresi proposed the magnet algorithm that uses a slower variant of GO-CR-GO topology that requires the use of broadcasts. In this algorithm, group owners attempt to connect to all neighbor groups, and that does not maximize connectivity, as we'll see in the evaluation section. Cassetti proposed the smart group formation algorithm that uses the GO-CR topology. It requires broadcasts and needs many messages and nodes. Furthermore, this algorithm may create three segments. From them, we identify the following problems. They need broadcasts. They only allow direct or indirect group owner connections, but not both. In particular, the magnet algorithm does not maximize connectivity, and the smart group formation algorithm may create separate tree segments. These problems open the door for improvements. Exploring the identified faults, we conceived the RedMesh network formation algorithm. We will show the algorithm operating over our scenario. Here it is, the scenario nodes. Now with a radio visibility network. Now with node identifiers. Here the algorithm starts running its first stage, the dominant node election stage. In this stage, nodes start by broadcasting their identifier. Then nodes with a higher identifier in the neighborhood become dominant group owners, or gods for short. They will be the cluster head nodes. Gods, the dominant group owners, are shown in yellow squares. The second stage is the cluster building stage. In this stage, the algorithm will form clusters, which are extended group formations. Dominant group owners start by enslaving neighbor nodes. Then these ones turn into group owners and try to enslave enslaved neighbor nodes. Now we have the clusters formed. We will delimit clusters with circular lines to improve visibility. Now you can see clusters more clearly. The third stage is the cluster neighborhood gathering stage. In this stage, gods will get information about cluster neighborhoods. The possible gateway nodes that are non-group owners start this stage by sending neighborhood information up to their gods. Gods promote some cluster gateway nodes to GOs, called lugs, to protect them from being used just from one cluster interconnection. We call it lugs in this presentation to make it short, but they are called LCGO UGs in the paper. Gods then send cluster neighborhood information up to the highest gods. This stage is then an ascending round. This stage only spreads information, and the scenario remains equal. The fourth stage is the main cluster interconnection stage. It is a cluster interconnection round. First, gods promote again some cluster gateway nodes to GOs. This is the second round of lugs. Then, gods will try to connect to lower clusters. They will only connect to clusters that are not reachable either directly or indirectly by neighbor clusters. Finally, they send cluster interconnection information to gods of lower neighbor clusters. This stage is then a descending round. This stage creates 7 cluster interconnections. They are the thicker solid or dashed arrows. After this stage, the scenario was 2 segments. The fifth stage is the final cluster interconnection stage, and it is the last one. It is the second cluster interconnection round. First, gods try to connect to higher clusters. They will only, again, connect to clusters that are not reachable either directly or indirectly by neighbor clusters. Finally, they send cluster interconnection information to gods of higher neighbor clusters. This stage is then an ascending round. This stage only created the cluster interconnection between nodes 3 and 17. However, now the scenario is connected in just one network. Here we will expose RedMesh main characteristics. It is targeted to maximize connectivity. It uses clusters. It uses 5 stages. It uses 5 interconnection rules, which use GeoGeo and the GeoCR-Geo topologies. It uses minimal cluster interconnection as it uses intermediated cluster connections. And it uses cluster gateway nodes in a protective way to improve cluster interconnection, the legs. We will detail the roles, the intermediated connections, and the legs in the next slides. About rules, there are 4 of them. Rule 1 covers the legacy client and group owner possibility. Rule 2 covers the legacy client and legacy client possibility. Rules 3 and 4 covers the dominant group owner and legacy client or group owner possibility. They are needed as dominant group owners are group owners that may have the Wi-Fi interface free. Rule 5 covers the group owner and group owner possibility. Therefore, the rules cover all nodes possible configurations. From them, the Rule 5 is a rule where the local group owner delegates all its slaves to enable it to connect to a remote node. Rule 5 is then a new rule in Wi-Fi-Direct network formation algorithms. Rules 1, 3, and 4 are also applied in the reverse direction if the direct version failed. The algorithm uses cluster intermediation to minimize cluster interconnection. That means that when connecting to a cluster, if there is a path to that cluster through some already connected clusters, that cluster will not be connected. With less connections, critical connections have more chances to succeed. To do that, gods only try to connect to clusters that they know that there is no direct or indirect connection by neighbor clusters. God analysis uses all the information going beyond the second level of cluster neighborhood. In relation to legs, they are legacy clients that are possible cluster gateway nodes that are also the unique local nodes to connect to 2 or more neighbor clusters, and they are promoted to be also group owners. If not, they could connect by being clients of another cluster, and then they would block future connections to other clusters. These nodes are set in the cluster neighborhood gathering and main cluster interconnection stages. We'll start the evaluation of RedMesh here. We used 1,250 scenarios up to 250 nodes. Now we'll discuss the use of the final cluster interconnection round. After the main cluster interconnection round, the algorithm presented an average of not fully connected scenarios of 7.12%. A not fully connected scenario is a segmented one. By scenario, here we mean the created network. After the final cluster interconnection round, the algorithm presented only 2.72% of not fully connected scenarios, confirming that the second cluster interconnection round improves connectivity. Now we'll discuss the evaluation of the R5 rule, the cluster connection by intermediation, and the cluster gateway protection. Regarding R5 rule, without this rule, RedMesh presented a result of 11.12%. Regarding cluster connection by intermediation, using only direct cluster connections, RedMesh presented 3.52%. Regarding cluster gateway protection, without using it, RedMesh presented 8.08%, confirming that these actions improve connectivity. Here we will compare RedMesh with existing Wi-Fi-Direct algorithms. Here we will use the average of fully connected scenarios, which for RedMesh is 97.28%. To emulate magnet, we only used the GO-CR-GO topology. We did not use the final cluster interconnection round, the cluster gateway protection LUGs, or the delegation rule R5. This setup achieved only 75.52% of fully connected scenarios. Even when all of these last three actions are activated, the result only raised to 84.82%. To emulate smart group formation, we only use the GO-GO topology. Even when we activate all the RedMesh actions, but using only that topology, we did not get a single fully connected scenario. Now we'll present the final conclusions. RedMesh creates mesh networks. These networks can exclusively use unicasts. RedMesh was tested on 1,250 scenarios with up to 250 nodes and achieved an average of 97.28% of fully connected scenarios, where all nodes reach all other nodes. We highlight that the best simulation, which is Magnet, achieved 75.52% of fully connected scenarios. Only that. As future work, we aim to improve cluster interconnection, reduce average short paths in the resultant networks, and we will make RedMesh tolerant to node sharing. Thank you.
Hi everyone, I'm Shuping Dang, working as a postdoc with King Abdullah University of Science and Technology. Today, I'm glad to present our latest research work jointly contributed by Cooperative University and King Abdullah University of Science and Technology, which is the first empirical study of the progress in wireless communication generations. This is the outline of the presentation today. So first of all, I will detail the background of the study and show its necessary and timely nature. Telecommunications have experienced a high-speed developing epoch in the past decades, and the constructive influence of the field on human society and technological development cannot be overestimated. Among a variety of branches of telecommunications, cellular communications have become ubiquitous and increasingly related to the daily life of everyone. Due to the importance of cellular communications, many financial resources and human capital have been devoted to academia for scientific research over the past decades. As a result of these investments, a number of groundbreaking communication technologies were invented and implemented to significantly ease our daily communications nowadays. These technologies include MIMO systems, OFDM, cooperative relaying, software-defined networking, and artificial intelligence for wireless communications. As the cellular concept become increasingly rich, actually there exists another voice questioning the usefulness of the physical layer academic research for future wireless communications. In particular, the relation between the physical layer research activities and the service improvements on practical cellular implementations. Before we are going to talk about the specific physical layer research, it is instructive to make it clear what physical layer is. The term physical layer originated from the open system interconnection model, that is also called OSI model, which is a conceptual model that characterizes the functions of telecommunication systems, regardless of its essential structures and implementation technologies. Compared with the conceptual OSI model, the transmission control protocol and the internet protocol model is a simplified version of the OSI model, and it consists of practical standards that allow communication over large-scale networks. This is a graphical overview of both the OSI model and the TCP/IP model, and also introduces related functions of each layer. So both models aim at standardization of various communication systems with unified communication protocols. Physical layer lies at the bottom layer of the OSI model, and it's also integrated in the link layer of the TCP/IP model. Together with the 5G enthusiasm, and now even the 6G enthusiasm, a number of novel physical layer communication conceptions, paradigms, and technologies have been proposed and investigated in depth. However, are they realistic or nothing but just hypes? There are many examples that there are a number of heated technologies in the past have finally turned out to be just a hype, and wireless communications are not exceptional at all. These hyped research topics and activities cost a lot of financial and human resources. As a result, the controversy and argument on the usefulness of the physical layer academic research are long-standing, and I personally believe should be constructive. So in light of this controversy from the research stakeholders, it is instructive to concern the following questions. So first, what are the factors determining the cross-national differences in telecommunication performance? Second, to what extent does the physical layer academic research affect the cellular network performance? Third, as an engineering discipline, what can we do to maximize the usefulness of the physical layer academic research? To provide some clues and preliminary answers to these questions in an objective manner, we employ a set of methodologies of econometrics to carry out the analysis in our paper. So to answer these three questions, we should first choose the powerful analytical methodology. And so this is widespread speculation that the impressive improvements in mobile communication over the past decades were preliminary achieved by network densification and the increase in spectrum resource, that is capital intensive growth pattern, instead of exponential growth pattern in published papers and information and communication technology or ICT patents, and that refers to a technology intensive growth pattern. So far, quantitative evidence is still lacking, and there's no consensus has been achieved yet. So as a applied discipline, the validity of the physical layer research for communications should be judged by its contribution to the cellular network performance. To evaluate practical scenarios in a unified and a simple framework, econometric analysis is a promising option. Econometric analysis is a midway path between a simulation and a control experiment. It is based on real-world settings instead of parameter assumptions, and it derives patterns and parameter estimates in a quasi-experimental manner due to the these properties, we adopt a econometric analysis as our analytical methodology in this empirical study. So Cooper's law leads to a speculation that a million-fold improvement in data rate over the past 60 years can be preliminary attributed to the densification of base stations, which accounts for 1,600-fold gain, and the expansion of radio spectrum, which accounts for a 30-fold gain. However, the progress in communication theory has just contributed to no more than a 10-fold gain. In light of Cooper's law, that the densification of infrastructure and the expansion of radio spectrum serve as the primary engine for network capacity improvement, we constructed the econometric model of throughput as given in equation 1. So the model in equation 1 implies that the increases in base station density and bandwidth have a proportional payoff in terms of throughput, which leads to the benchmark empirical model of throughput as given in equation 2. So based on the empirical model constructed in equation 2, we can employ the econometric analysis to analyze and discuss the empirical results. So in particular, the empirical model given in equation 2 is a reduced form linear regression designed to assess the determinants of cross-national differences in the performance of cellular communications. We collect the latest data sets to construct a comprehensive country-level database, which covers 138 nations or regions that are the observations, and over 100 performance matrix in 2018. So matrix that leads to justifiable and robust empirical regularities are selected as key matrix. For clarity, the definition and the sources of the key matrix are listed in this table. So for instance, considering the causal effects of base station density and the spectrum in use on download speed, the figure presented in this slide visualizes the observations from our datasets and the corresponding parameter estimates. In these two simple linear regression examples, the standard ordinary least square method finds the parameters that lead to the minimal prediction error. Overall, both variables are significantly correlated with the download speed. Relatively to the base station density, the spectrum in use has a higher degree of explanatory power, so which is represented by the R squared value and accounts for a greater cross-national variation in the download speed. This evidence indicates that Cooper's law may have emphasized the relative contribution of base station densification. So to improve the overall fitness, the regression model needs to incorporate other performance determinants and take a functional form, complying more with the theoretical derived form. The table shown in this slide displays the ordinary least square estimates for multiple linear regressions, in which the first column is associated with the benchmark estimation, and the other columns are related to the estimations used alternative sets of metrics. According to the first estimation, mobile download speed is positively and significantly correlated with the number of installed telecommunication towers. Each additional telecommunication tower per 1,000 subscribers increases the download speed by 4.14 megabits per second. So this also implies a pronounced effect of telecommunication infrastructure on cellular network. Similarly, each 1 megahertz increase in bandwidth leads to a 0.06 megabits per second increase in the download speed. overall base station density and the spectral resources can explain 41% of the cross-national differences in mobile download speed, which validates the explanatory power of the two-factor model and can also indicates the existence of other performance determinants. Through the key findings presented and discussed in the above slides, we need to confront the fact that impressive performance improvement in the past decades is only marginally attributable to the physical layer research. We identify three stakeholders of the physical layer research, which are the policymakers, funders, and the researchers. And we have a series of suggestions for them based on the facts and the data we obtained. So first, there's no doubt that administrative intervention has a significant impact on applied disciplines, including wireless communications. So policy orientation should focus not only the prospective wireless technologies that do not have a solid foundation nowadays, but also on the practical wireless technologies that can benefit the society in a near future or in a predictable future. Also, when assessing a project proposal applying for financial support, funders should pay attention to not only how many papers will be published or how many patents will be applied at the end of the project cycle, but also the possibility and vision of the technology transfer, as well as how, if it is possible to commercialize the technology. The assessment of potential market value and practicability should be based on the real needs of the end users, which is a very important reference point for funding applications. It is highly suggested to also add these economic features as a part of funding strategies and carry out long-term tracking and evaluation of them. A new evaluation system of the research outcome could be constructed to evaluate how good a project has been from both technological and socio-economic perspectives. To some extent, telecommunications are becoming a subject of hard to understand mathematical models and series, which renders the field gradually divorced from reality. So many communication series are barely understandable to telecommunication practitioners, and their applicability has not been proven yet. Consequently, so new research directions are the key to restore the discipline to its former. The real problem is not why we have devoted so much to the physical layer research, but why we have so far de-emphasized the non-physical layer research and the needs from the end beneficiaries. Accordingly, the wireless research community needs to pay more attention to alternative approaches to the fundamental questions of telecommunication science. And the beneficiaries should also have a voice in shaping research roadmaps. Researchers with different backgrounds should also be encouraged to address the same problem using approaches from different subjects, just as the empirical methods we used in our study that can serve as a bridge between academic and real-world problems. And we borrow that a tool or technique from econometrics. So now we reach the summary of this empirical study. So in this paper, we employed econometric methodologies to investigate the usefulness of the physical layer academic research in terms of their contribution to the cellular network performance. The empirical analysis confirmed that the main contributor to the service improvement is the densification of cellular network. However, only a marginal portion of the service improvement can be attributed to the physical layer academic research. So turn to the core issue on the discussion. Is physical layer research dead? In conclusion, no. The physical layer research is not dead yet. as the marginal return of the physical layer research remains statistically significant. And there is indeed a huge potential for performance improvements by research efforts. However, we also need to confront and react to the diminishing return of the physical layer research. This study is the first one to employ a empirical analysis to evaluate the progress in wireless communications. Based on the actual observations, researchers are able to answer real-world problems, such as the relative importance of academic research, other than just being confined to the mathematical problems of interest only to academics. This study explores a new angle to quantify the marginal contributions of base station density, spectral resource, and the research output in promoting telecommunication performance. And there are also 3 key references recommended for the attendees to this talk, and you may follow these references if you are interested in this topic and would like to follow our empirical research. All right, that's the end of this talk. Thank you for your attention and listening. And please feel free to email me if you have any questions. This is my email.
Hello everyone, my name is Stefanos, and today I will talk about Kairos, a self-configuring approach for short and accurate timeouts in the Internet of Things. So, what is the Internet of Things? Well, it typically consists of sensors and actuators, which enable the remote monitoring and control of physical processes and environments. These devices are typically resource constrained in terms of computation and power, and they connect with each other, forming wireless sensor networks in order to achieve together common application goals. In the next slides, I'll talk about 2 examples of such applications. The first example consists of an airbag manufacturing plant for cars. Now, as you can see here, there are several production lines, and because airbags are such a critical feature, there are strict regulations in terms of their quality. In particular, when the number of defect airbags exceeds a certain threshold, then all the airbags from the current batch need to be discarded. So each of these production lines is equipped with a sensor that measures the quality of the airbags, and they periodically transmit data to the gateway, from where it goes to the application, and the results are shown on a display. These sensors are typically connected together, as you can see here, forming a wireless mesh network, and as is visible from the image, the different communication links, they differ in terms of lower and upper bounds for the communication delay. So here, for example, packets can follow different paths on the network, which would result in different arrival times at the gateway. Now, this raises the question, when should the application stop waiting for sensor data to arrive? And that question is important because when the application decides sensor data will not arrive, production needs to be stopped in order for somebody, a technician for example, to go check on the sensor. So we certainly don't want to pause the production for nothing, which could be the case if the application does not wait long enough, because maybe then events will arrive later due to this delay. However, if the application is waiting too long to make this decision, we potentially will have to throw away a whole bunch of airbags that have been produced in the meantime, should the number of defect airbags exceed that threshold. For the second use case, I'll talk a bit about smart traffic lights. And the goal here is to automatically adjust traffic lights transition windows based on how busy the intersection is, in order to optimize the traffic flow. So also here, each of the traffic lights is equipped with a sensor that transmits data periodically to a gateway. And as you can see here, the delay also varies for different communication links. And an important difference with the previous network is that here all of the sensors are connected directly to the gateway. That's also referred to as a wireless star topology. This also raises the question, in this use case, when should the application stop waiting for sensor data to arrive? Also here, when the application decides to stop waiting, because sensor data will not arrive, then the intersection needs to be closed in order for somebody to go and check on the status of the sensors. So closing the intersection for nothing is obviously a bad thing, and that can happen if the application does not wait long enough. However, if the application is waiting too long and in the meantime there are missing events, this can not only lead to suboptimal traffic, but also accidents. So what both of these use cases and such use cases have in common is that they have strict requirements, both in terms of tolerance to missed events. It's very low. That's also referred to as a high completeness requirement. And in terms of the timely detection of event non-arrivals. And that's referred to as a high timeliness requirement. And the reason it is difficult to simultaneously achieve these two requirements is because of this varying delay that is so typical for IoT wireless networks. This delay is partly due to the network itself, especially in the case of wireless networks. And as you saw, for example, in the case of wireless mesh, packets can propagate across different paths, which lead to large variations in delay. A second factor is the device itself. These devices are not perfect, and typically, for example, when they're configured to transmit periodically, they do not transmit at exactly the period they've been configured. Sometimes they send slower, and sometimes they'll send faster. And that can depend on several factors, for example, whether or not the device is currently busy doing something else, or if its clock is drifting, etc. Here you can see, just to get a feeling, the impact that the underlying network technology has on the characteristics of these event inter-arrival times. So you can see for some MAC layers, for example, if you look at the middle plot, the inter-arrival times vary in the order of several seconds. While for other MAC layer protocols, as you can see on the left and the right, it varies in the order of some milliseconds. I'll next talk a little bit about related work in this field. That's important also to clarify a bit better what the limitations are currently in order to sketch the requirements for our contribution. So the first of these related works is PropSlack. And in PropSlack, the user specifies the sliding window query frequency. That's essentially how often the application executes, well, processes events that have arrived. So it's essentially this timeout. And the user or the developer also specifies the missed event ratio budget. That's the tolerance of the application to missed events. Now what PropSlack does, it's a probabilistic approach, and when it's time to process the events, it will either postpone the processing by a dynamic offset, that's what's called the slack, or it will process the events, possibly with some missed events, using up this budget. Now, two limitations of PropSlack is that on one hand it relies quite heavily on the developer, who needs to specify at compile time what is essentially the timeout, this sliding window query frequency. And that's not always feasible because, for example, in some applications, like we saw in the manufacturing plant, during peak hours, you might want to process events faster than you do outside peak hours. And you cannot simply express that behavior with one timeout in advance. Furthermore, it requires some additional configuration in order to maintain these delay models for each of the sensors. But as we also saw for different technologies, these delay models, they can look quite different. And it's certainly non-trivial for the developer to know in advance how often these models should be refreshed. And secondly, and perhaps most importantly, PropSlack's evaluation shows that it does not consider completeness constraints that are higher than 90%. Or in other words, it does not consider applications that require less than 10% missed events. So to summarize a little bit, PropSlack does achieve timely detection of event non-arrivals. However, it does not achieve the satisfaction of high completeness constraint. So it does one of the two. Next, I'll talk about Chronos, which is a middleware that's also related to this trade-off between completeness and timeliness. And in the case of Chronos, what the developer specifies is only the application's tolerance to missed events. And that's, in other words, the completeness constraint. And what Chronos does is it enforces this completeness constraint by automatically adjusting the timeouts for event arrivals. The prediction technique it uses to determine these timeouts, we can see here on the top of the slide. It's this formula. And each of the timeouts is essentially equal to a smoothed arrival time plus a number of times, that's the sensitivity factor K, the smoothed arrival time variance. And now this formula inspired by how TCP handles a similar problem, in which case the sender transmits a message to the receiver, and the sender needs to decide how long to wait for the acknowledgement to arrive for that message before he would retransmit it. A key difference between the two, however, is that in the case of TCP, k has a fixed value, while in this case, because we can have different completeness constraints, k is a function of the completeness constraint. And in particular, the way k is determined for a range of completeness constraints is by examining the network in advance, up to several weeks, under various conditions, so that we can find the smallest k that would satisfy each of the constraints. And this value is then over-provisioned by doubling it for robustness. Now, this works well, as the evaluation results show. However, for really high completeness constraints, it leads to impractically large timeouts. So looking back at the requirements, Kronos can satisfy applications with very low tolerance to missed events. However, that implies that it cannot do high timeliness at the same time. So there is still a need for an approach that can satisfy both these high completeness and high timeliness requirements simultaneously, while at the same time not relying on the user for configuration or pre-configuration, which can be an error-prone process that can lead to inefficient solutions. And I'll talk a little bit about Kairos, which aims to tackle these gaps. Now, for Kairos, we build on top of this formula that's already been established. However, what we do differently is we change the sensitivity factor k dynamically. And that's based on the hypothesis that even to satisfy high completeness constraints, a large k is only necessary to cope with large variance in the delay. Otherwise, a smaller case would also suffice. And this fits well with a closed-loop approach, since we want to regulate this k based on the current performance or the current missed event ratio. And that's the approach we followed in this paper. In particular, the input signal, which is given by the user, is the completeness constraint, or actually the upper bound of the missed event ratio. The error signal is calculated based on this input signal and the feedback signal, where the feedback is the current missed event ratio. And based on that, the controller computes actually the next sensitivity factor that will be used to predict the timeout. So I'll go into a little bit more detail on how this target missed event ratio is computed. And essentially what the target missed event ratio is a new upper bound, different than what the user specified. And the way we compute this is very simple. So for example, if the user gives an upper bound of 10%, say that the current missed event ratio is 2%, then we will aim for a missed event ratio upper bound of 8%. If the current missed event ratio would be 6%, then we aim for a missed event ratio upper bound of 4%. So the goal there is to keep the missed event ratio as close as possible to the middle of the interval between 0 and the original completeness constraint that was given by the user. And the reason we would like to keep it in the middle is because it still leaves us some room to make mistakes, but we're not being overly careful in order to hurt the timeliness without having to. So once we have this target missed event ratio, or this upper bound for which we want to aim, we find the smallest k that would satisfy that target missed event ratio. And the way the controller does this is by starting the k at a very small value, in this case 0. And in every step, it increments this k by a small step. And it tests if in a window of recent events, this new k would satisfy this target missed event ratio. If it does, then it returns this k. Otherwise, it increases this k with that step, and it tries again. And it will stop either when this is leading to no more improvement, so we've converged, or when the actual k is found. Now, once this k is found, it is used in the prediction technique, as I already mentioned, and we compute essentially the next timeout. In practice, all of this takes in the order of milliseconds to compute, so it's still very fast. Now, I'll talk a little bit about how all of this is implemented. We chose to implement this in Python 3.6 because that was also the implementation of one of the related work, in particular Kronos. So it made it easy to insert our approach into that system and test the results. And in particular, we extended the class diagram of Kronos' architecture with a new class called Advanced Stream, which implements our algorithms. All of this runs on a Raspberry Pi 3, which is similar in resources to what you would expect from a typical IoT gateway. So it runs quite close to the IoT network, which has certain benefits in terms of response times. Now, for the IoT wireless technologies, we used two standard networking technologies. One is Smart Mesh IP. That's a wireless mesh network, and it consists of 29 devices in total, out of which 20 are actually sensing. And this is typically what you would use in the first use case that I talked about. For the second testbed, we used LoRaWAN that forms a wireless star network. And then for there, we used 50 devices. And it's what you would typically find in smart city use cases, like the second one that I mentioned. So we've conducted several experiments on top of these testbeds, which I'll go into detail next. And we've compared the performance of Kairos against state-of-the-art across two dimensions, heterogeneity and dynamism. Now, for heterogeneity, we identified 4 sources, which are in line with what's been previously used in the literature for evaluations in this field. The first is a range of completeness constraints. The second is for different network topologies. In particular, in one case, we deployed all of the devices close to the gateway, while in the other case, we deployed them across 3 departmental building floors, so quite spread out. For different MAC layers as well, that relates to how I showed in the beginning of the presentation that based on the underlying MAC protocol, the delay characteristics can be different. And finally, for different sampling periods, in case sensors sample every few seconds, which can also be every few minutes. So here we can see the results, and if you look at the left, you can see for a range of completeness constraints, the prediction error of Kronos compared to Kairos. And what you can see here, if you focus on the highest completeness constraint, is that in the case of Kairos, it is satisfied with an average prediction error of less than 10 seconds, while in the case of Kronos, this is hundreds of seconds, so an order of magnitude larger. And so basically what this means is that for the same accuracy, Kairos requires less than 10 seconds to decide an event will not arrive, compared to Kronos, which requires hundreds. So there is a very big gain in terms of timeliness. And similar trends hold in the rest of the graphs, so I will not go into too much detail here. Instead, I'll talk a little bit about the dynamism experiments that we did. And again, we identified 4 sources of dynamism, which are in line with what's previously been used in related work. The first of which is network size. In particular, devices can fail and leave the network and they can join later, so that's something that can change at runtime. The sampling period is also something that can change at runtime. Typically in IoT networks, for example, sensors may sample faster during the day compared to the night. The spreading factor is a parameter in LoRaWAN networks that determines how far your device can reach, so if it's moving away from the gateway, it will also change at runtime. And finally, the payload size can also change based on how large or small the value that's being measured is. So if we look here at the results for a dynamic network size, we can see by looking at the top subplot that neither of the approaches violate the constraint, but in the case of Kairos, there are still some missed events, but they're all well below the boundary that you can see by the black line that's indicated by the arrow. But by missing some events here and there, we can see very important benefits in terms of timeliness when we compare the two approaches. And similar to before, the average prediction error of Kairos is in the order of a few seconds, while for Kronos it's hundreds of seconds. And in particular, when the network size changes at runtime, that can jump in the case of Kronos up to thousands of seconds, while for Kairos it still remains in the order of seconds or tens of seconds. So up to many orders of magnitude better performance in terms of timeliness for Kairos compared to Kronos. Similar trends hold for the other experiments, so I won't go into too much detail here. You're free to ask, of course, in the questions, or you can look at the results in the paper. Instead, I'll conclude my presentation. So we've contributed to the literature with Kairos, which is a lightweight self-configuring approach that satisfies both high completeness and high timeliness requirements that, as we saw, several use cases can have. And overall, it leads up to 2 orders of magnitude smaller timeouts compared to state of the art, if not more, as you just saw in that case of dynamism, where the network size changes at runtime. So thank you very much for your attention. I hope you enjoyed the presentation, and feel free to ask any questions.
Hello, I'm here to present our paper called Visually Defined Real-Time Orchestration of IoT Systems. Our paper is focused on the IoT field, a field that has been growing for these past years. The increase in the number of devices with reasonable computing power, sensing and connectivity capabilities has allowed for a great rising in IoT application and approaches. Many tools for building IoT systems use visual elements, more specifically visual programming, which lowers the learning curve and has the goal of facilitating the development process. One of the most famous tools with this approach is Node-RED. Node-RED is a centralized system, as most visual programming environments are. A centralized system has a single or main instance that executes most or all computation tasks on the data provided by other devices. In order to understand and discover existing visual programming tools applied to IoT, we made a systematic literature review. From the 28 analyzed tools, 16, the majority, are centralized and don't mention any kind of license, so they can't be considered open source. Many are similar between them, where some of the tools are extensions or upgrades made to already existing tools, like Node-RED. Based on the conclusions from the systematic literature review, we can establish that most mainstream tools for developing IoT systems employ centralized methods of computation, where a single or main component executes most of the computation on the data provided by edge devices. This brings several consequences, such as the existence of a single point of failure, which is the main component that executes most of the computation. Data is being transferred across boundaries without being needed to or even violating legal constraints, which ignores the no-cloud and local-first principles that advocate for the storage of data and execution upon it locally. In addition to this, there are computation capabilities of the edge devices that are being ignored. In regards to decentralized visual programming tools applied to IoT, 4 tools were analyzed on several aspects. All tools claim that they take advantage of the computational resources of edge devices. However, some of them impose limitations on these types of devices. The DDF solution requires that all edge devices have x86 or ARM-based Linux to be able to run Node-RED on them. On the other hand, the tool FogFlow and UFlow transforms tasks into executable code that can run on more limited devices. For a successful automatic decentralization, the system must know the capabilities of the available devices. Some of these tools implement this feature by communicating the edge device's capabilities to an orchestrator. However, they require that the developer introduce these capabilities manually, which is not scalable. A robust decentralized system must adapt to an availability of devices. Most tools claim that they implement this feature. However, only the tool BDFlow evaluates it. As it can be concluded, there seems to be some promising decentralized VPLs applied to IoT. However, some of them are incomplete or don't even provide any source code or executable. Our goal was to develop a prototype extending Node-RED that enables IoT devices to communicate their computational capabilities to the orchestrator, which, in its turn, will be able to automatically partition the computation and send the created tasks to the devices, leveraging their computational power. The prototype must be able to convert computational tasks into runnable code, as well as self-adapt to any changes in the devices. We aim to build a system that complies with author desiderata, and we evaluated it based on several attributes: resiliency, which we measure by injecting failures and measuring the recovery patterns, efficiency, which is calculated by measuring the latency taken to react to certain events, and scalability, which was measured by adding or removing devices in different scenarios and assessing the overall system's behavior. These attributes were compared against a system using the current development branch of Node-RED. The solution contains two modules, the decentralized Node-RED and the developed MicroPython firmware running on the edge devices. The devices start by announcing themselves and their capabilities through MQTT topics, which will be listened to by an orchestrator running in Node-RED. This orchestrator is responsible for decomposing the workload into tasks, generate scripts of code, and send them to each device. It will then ping the devices to keep tabs on their state. Node-RED originally communicates between nodes by using JavaScript's event emitter, but this approach is prohibitive in a decentralized architecture. It was then changed to allow communication through MQTT topics between nodes, which are generated between the systems when the system first starts. On the device's side, they execute a MicroPython firmware. This firmware includes an HTTP server, which is responsible for receiving a script of code, saving it on memory, and later executing it, as well as answering to the orchestrated ping requests. In addition to this, it has an announcer behavior which is executed when first starting up or after a failsafe, in which the device will send through an MQTT server topic its IP address, capabilities, and if it had recently failed. This failure flag is due to the failsafe mechanism, which is triggered when the device fails, mostly due to out-of-memory errors. These errors are common since the goal was to use limited devices with small amounts of memory, and scripts sent from the orchestrator might surpass its memory capability. On the Node-RED side, there is a registry node responsible for listening the announcements of the devices. These announcements data, as well as the nodes of the flow, are passed on to the orchestrator. The orchestrator decomposes and assigns the nodes to each device, generates a MicroPython script for each one, and sends it. It also probes the devices for their status, and if any change occurs, it will start the orchestration process again. The orchestration and assignment logic uses a greedy heuristic that takes into account the device's capabilities and the predicates and priorities of a node. The predicates are constraints that cannot be violated, and priorities are requests that are advisable and recommended but can be ignored if needed. The assignment algorithm has two phases, filtering and scoring. Given one node, the filtering phase will filter the available devices and return the ones that comply with all the predicates of the node. The scoring phase returns a device that can comply with the biggest number of priorities of the node, has less nodes assigned to it, and is more specific in its capabilities to the predicates of the node. When executing the system, the devices will first start to announce themselves to Node-RED. When deploying the flow in Node-RED, the orchestrator will decompose the flow, assign nodes to devices, and generate and send the script files. If the orchestration is not successful, it will try again until it is. When a device becomes unavailable, recovers, or a new one appears, the orchestration loop will restart. To evaluate our architecture and prototype, we experimented with two scenarios with several experiments each. We use virtual and physical setups, such as Docker container running a Unix-compatible version of MicroPython and microcontrollers with a MicroPython firmware connected to the same Wi-Fi network. We measure several metrics such as uptime, number of nodes assigned, payload size, and others. In this image, we can see a testbed used for one of the scenarios. The first scenario presents a flow with 3 temperature and humidity sensors that must reach a conclusion on the state of temperature and humidity of the room. The conclusion will result in an action by the air conditioner. On this first scenario, we made several experiments in which the first 2 consist of sanity checks, where we assessed that the system was working as expected. In the experience A, the goal was to evaluate if the system is able to recover after device failures. During the experience, the devices were turned off one by one until only one was left running. As it can be observed, When a device goes down, its nodes are assigned to the available devices. Only when one device is left running, it has all the nodes assigned to it. This experience was repeated with physical devices. The behavior was similar, but in the end, the last standing device failed safe due to out-of-memory errors. This was expected since the physical devices were more memory constrained than the Docker containers. The Experience C goal was to evaluate the system's capability of adapting when devices fail and recover inconsistently. Devices 3 and 4 fail early and the system recovers, assigning their nodes to the other devices. Device 4 later recovers and fails, but the system didn't react since this event was fast. This is not negative, since it would be an unnecessary reorchestration. However, this experiment shows that the fast failure and recovery of the devices can be costly to the system, since the repetition of this behavior might cause a reorchestration loop. The device's memory constraints can negatively impact the system's behavior. This can happen when a device receives a bigger MicroPython script that causes out-of-memory errors when trying to save it to the SPI flash. This experiment evaluates how the system adapts to this limitation. The devices 2 and 4 are memory constrained. As it can be observed, they were assigned less nodes, which happened after they fail-safed. When they recovered, they communicated this failure to the orchestrator, which assigned less nodes to them. This demonstrates that the system can adapt to the memory constraints of the devices. In addition to dealing with memory-constrained devices, the system must also adapt to memory leaks in the devices, which might easily occur with faulty firmware or degraded hardware. In this experiment, the device 2 was modified to cause out-of-memory errors after a random period of time. The system must exclude this device from their assignment process. As it can be observed, the device is constantly failing because the orchestrator is assigning less nodes to the device on each orchestration loop, until it finally excludes it from the process. To verify the resiliency of the system to memory errors, it was introduced in the flow a node that causes errors in specific devices. The system diagnoses that the error is caused by a device, which is not. However, it ends with the working solution by assigning the node to a device not sensible to its errors. This experiment's goal is to test the system's limits by constantly introducing failures in the devices. Each second, each device has a 5% probability of being unavailable from 0 to 10 seconds. During this time, the device won't respond to the orchestrated requests, and when it recovers, it will announce itself to the registry. This experience demonstrated that after the first failures, the system becomes unstable. Even after all the devices are available for a short period of time at 100 seconds, the system is constantly reorchestrating. This is due to the fact that each device failure and recovery causes a possible reorchestration in the system. When an orchestration ends its assigning, the solution is already outdated. This is a current limitation of the system, which makes it vulnerable to a denial-of-service type attack in the form of activity access in the statuses of the devices. The constant reorchestration is also costly to the devices, causing an overload of requests that don't correspond to a workable solution. To benchmark our system, we developed a scenario where a message must be passed through a number of devices and the time it takes to reach the final point is measured. Each device only passes the message to the next one. We built 6 different configurations using both virtual and physical devices with different types of communication. It can be observed a considerable difference in latency between using events and MQTT topics as methods of communication, and an even bigger difference between containers running on the same and different hosts. This is expected since this latency is introduced by the communication channel. There is also latency introduced by the physical devices and their Wi-Fi cards. With these results, we observe that our prototype is slower than the centralized and original Node-RED. However, the latency introduced is due to the communication channel, and the developed models introduce little latency to the whole system. During this proof of concept, we haven't made any slight attempt to optimize this metric, so we are confident that this could be easily dealt with. Given the results from the experiments, we can conclude that our system is moderately robust by handling device failures and memory constraints dynamically. It is elastic, which was shown in experiments by handling a moderate-sized IoT system with devices being added and removed in runtime. And finally, the system is less efficient compared to a centralized node-RED. However, most of the latency introduced comes from the communication channels, which is unavoidable in a decentralized system. Our approach has some improvements to be made, such as the algorithm used to assign nodes among the available devices, which currently may fail to find a suitable solution. There is room for optimization by bypassing the communication substrate between nodes assigned to the same device and trying to increase the likelihood of connected nodes being assigned to the same device. There are also some limitations that were mentioned before, such as the system constantly reorchestrating when a device fails and recovers constantly, as well as the fact that the orchestration redeploys the entire system and does not attempt to take into consideration a set of minimal changes. Lastly, our proof of concept is slower than the original node-RED due to its decentralized nature and the communication channel, which can be optimized. You can find our implementation in this GitHub repository, and we will be delighted to have your feedback. Thank you.
Thank you for watching. This is Chen coming from the Institute of Information Engineering of the Chinese Academy of Science. This paper purports a novel multi-hop relay scheme where D2D users cooperated with the cellular users. These contents will be included in my presentation. First, I want to introduce about NOMA. NOMA is a new kind of multiple access technology. NOMA exploits the power domain to multiplex users. As it is shown, UE1 is the cell center user and UE2 is the cell edge user. At the transmitter side, UE2 is allocated with more power than UE1. The BS transmits a superimposed signal of the two users. At the receiver side, UE1 uses the successive interference cancellation technology. It first decodes the message of UE2 and then subtracts it from the received signal. On the other hand, UE2 decodes its message directly by regarding the message of UE1 as noise. Then I will introduce some basic ideas for the cooperative NOMA. So what is cooperative NOMA? Cooperative NOMA is first proposed by Ding Zhiguo, since the cell center user must first decode the cell edge user's message before decoding its own message. For example, in this figure, UE1 must first decode the message of UE2. Therefore, the cell center user has the knowledge of the cell edge user's message and can serve as a relay for the cell edge user. The so-called DC NOMA refers to D2D added cooperative NOMA. It incorporates C-NOMA into D2D communication, in which a D2D transmitter is utilized as the relay to help the transmission of a cellular user. DC NOMA encourages D2D users to participate in the cooperation. A D2D user adopts NOMA to simultaneously transmit the signal of a far user and that of its own. In the 19th paper, The maximal ratio combining the MRC technology is applied to improve the quality of received signal, and the outage probability of the cell edge user is given, but not in the closed form. In Tan's paper, the cell edge user's signal is split into two symbols for transmission, and the ergodic sum capacity is investigated without MRC technology. However, existing researchers only consider the D2D transmitter as the relay for a cellular user, which neglects the prior information owned by the D2D receiver. Our contributions are listed. We propose a novel multi-hop relaying scheme for D2D integrated SUMO system. Different from the above researches, we introduce the DR as an additional relay and use MRC as the receiver of the cell edge user to a more diversity gain. We derive the closed-form expressions for the cumulative distribution function of the SRNR at all users. Accordingly, we present the analytical expressions of the ergodic capacity and outage probability of the proposed scheme. Simulation results are provided to verify the accuracy of our analytical derivations. It is shown that our proposed scheme outperforms conventional two-hop relay schemes, especially when the cell edge user locates far away from the BS. As depicted, we consider a downlink cooperative relaying system with one BS and two CUs, namely CU1 and CU2. Furthermore, a D2D pair is considered where a DT communicates directly with the DR. It is assumed that each node is equipped with a single antenna. In addition, all nodes operate in the half-duplex mode with decode and forward strategy. For the notation simplicity, the BS, CU1, CU2, DT, and DR are denoted by subscript B, 1, 2, T, and R respectively. Then, the channel coefficients between the node I and node J can be denoted as Hij. For instance, the channel coefficients between the BS and CU1 is denoted as the HB1. The complete process of our proposed scheme are achieved in two phases. Example, the even time slot and the odd time slot. In the even time slot, for example, the 2nth time slot, the BS superimposes the signal of CU1 and CU2 and forms a composite signal. The BS then broadcasts the composite signal. At the same time, DR acts as a relay and transmits the signal of the CU2 of the last time slot. It can be learned from the right figure that CU1 and DT receive S2 as well. However, since CU1 and DT already decode the signal of CU2 in the last time slot, they can cancel it in the 2nth time slot and are not interfered. Therefore, the received signals at CU1, DT, and CU2 in this slot can respectively be given by the equations at the right part. In the 2n plus 1th time slot, it is supposed DT can successfully decode the S2n. Then it can act as another relay and transmits a composite signal of S2n and SRN to DR and CU2, where PT denotes the transmit power of DT. Similarly, beta is the power allocation coefficient. The received signal at the two receivers, DR and CU2, can be given by the equations on the right. Based on the NOMA power allocation protocol, SRC is performed at CU1 in the even time slot. Therefore, CU1 first decodes the data of CU2, and then the SINR for CU1 to decode S2N can be expressed as the first equation in the green circle. If S2N can be perfectly decoded, CU1 subtracts HB1S2N from RB1 to N and decodes its own signal. The SINR for CU1 to decode S1N is given as the second equation in the green circle. Meanwhile, DT directly decodes S2N by regarding S1N as noise. The SINR for this is given as the equation in the yellow circle. After implementing MRC, CU2 combines RT2 2N plus 1 and RR2 2N plus 2 to decode its own signal. The SINR for CU2 to decode the S2N is given as the equation in the blue circle. In the old time slot, DR performs SRC and first decodes S2N. If S2N can be perfectly decoded, DR then decodes its own signal SRN. The SINR for DR to decode the S2N and SRN are respectively given as the first and second equation in the right circle. Based on the DF protocol, the end-to-end rate is dominated by the weakest link. Furthermore, CU1, DT, and DR must successfully decode the cell edge user's signal before decoding their own signals. Therefore, the achievable rates at CU1, CU2, and DR of the system are given as the top three equations. The factor 1 divide 2 is due to the fact that CU1 and CU2 decode their own signal only in even time slots and DR decodes its own signal only in odd time slots. In a two-hop relay scheme, the BS transmits a composite signal of S1 and S2 in the even time slot, and DT superimposed SR on S2 in the odd time slot. Therefore, the achievable rates are given by the bottom three schemes. The probability density function and the complementary cumulative density function can be given as the two equations. The outage probability is defined as the probability that achieved rate is below than a target rate, using the RTH1, RTH2, and RTHD to denote the target rate of CU1, CU2, and DR respectively. Then the thresholds of SINR at these receivers can be denoted as the three equations. The probability density function and the complementary cumulative Then we will give the expressions of the outage probability. The outage events for CUE is that CUE fails to decode S1, and the outage probability is given as this page shows. Then the outage probability of S2 can be divided into two cases. Case 1 is that DR fails to decode S2, and case 2 is DR can successfully decode S2, and the received SNR are respectively given as this page. Then the outage events for CU2 can be case 1, DT cannot decode S2, and case 2, DT can successfully decode S2, but DR cannot decode S2 and CU2 cannot decode S2, or DR successfully decode S2, but CU2 cannot decode S2. So the outage probability of CU2 is given as the equations presented in this page. And after some algebraic manipulations, we divided it into two cases for calculation, and one of the cases is presented at the page. The complex proof can be found in our paper and is omitted here for saving time. So the complementary outage events for DR is that DT can successfully decode S2 and DR can successfully decode S2. Thus, the outage probability of DR is given as this. So next we will talk about the ergodic capacity. The ergodic rate of S1 is given as this. Similarly, the ergodic rate of S2 is given as this. However, it is impossible to obtain a closed-form solution to this integration, so we use numerical integration to verify the correctness of our analysis. Then, similarly, we provide the capacity analysis of the DR. Since the outage probability of CU1 and D2D user are the same in the two comparing schemes, we investigate the outage probability of CU2 versus the transmit SNR of the BS in figure 3. Since the outage probability of CU1 and D2D user are the same in the two comparing schemes, so we investigate the outage probability of CU2 versus the transmit SNR of the BS in this figure. Moreover, we consider three topologies. Fixed power allocation are considered with alpha equals to beta equals to 0.1. It can be seen that the multi-hop relay scheme outperforms the two-hop relay scheme for all the three topologies. Moreover, the performance gap is especially remarkable for topology 1. This is because the effect of diversity gain becomes more evident when CU2 locates farther away from the BS. Thus, the multi-hop relay scheme can enlarge the network coverage. Furthermore, our analytical results match perfectly with simulation ones. In this figure, the ergodic sum capacity versus the power allocation coefficients are investigated with different transmit SNR. In the top subfigure, the impact of alpha is presented assuming beta is equal to 0.1, whereas in the bottom one, the impact of beta is presented assuming alpha is equal to 0.1. It is observed that The multi-hop relaying scheme outperforms the two-hop relaying scheme in all combinations of power allocation coefficients. Further, the performance gap between the two comparing schemes becomes smaller when the power allocation trends to be equally allocated. Therefore, proper power allocation is needed for the proposed scheme to earn a better performance. In this paper, we propose a novel cooperative scheme for D2D integrated SUMO system. By taking both DT and DRS relays, the cell edge user applies MRC to improve the quality of the received signal. Closed-form expressions for the outage probability and algebraic sum capacity of the proposed solution are derived. Simulation results indicate that the proposed scheme can achieve lower outage probability and higher sum capacity compared with existing two-hop relaying schemes. To further enhance the performance, optimal resource allocation policies will be investigated in our future work. Thank you for listening. If you have any questions, you can contact me by this email address. Thank you.
Hi, I am Michele Albano from Aalborg University, and I will present the paper Generation of Realistic Activity Scenarios for SUMO. The work was done together with Mr. Carlsen, Mr. Rasmussen, Mrs. Sorensen, and Mr. Jensen. Probably the most important open source simulator for vehicular and pedestrian traffic is nowadays SUMO. The simulator is able to perform realistic simulation of vehicular traffic, but it needs to be configured properly to be able to provide all these benefits. Typically, the configuration of SUMO is done in two phases. The first phase is the creation of a network topology. In this case, we're meaning a network of roads, pedestrian and bicycle ways, railways, etc. In terms of SUMO, this network is composed by edges, which are, let's say, all the segments that compose the roads, the pedestrian and bicycle ways, the railways, etc. The second phase is the configuration of the traffic demand, and we mean vehicular and pedestrian traffic demand. This demand is represented in terms of a set of start and destination edges for each simulated traveler and a departure time for the route. Then SUMO will use this configuration to generate the routes, which are the set of edges that each traveler will move on. The first step can be done by creating a totally synthetic scenario, but most often it's more interesting to download an existing real map, for example from OpenStreetMap, and then apply the tool NetConvert, which is part of the SUMO toolsuite, to transform the format of OpenStreetMap into a set of edges that SUMO can use for the simulations. The second phase is more tricky, probably, because the definition of a traffic demand needs to set up a large number of parameters. The easiest way to do that is to generate a completely random scenario. For example, with the tool random trips. Another way is to create an activity-based pseudo-random scenario. For example, using ActivityGen, SUMO PI, or Saga. In this case, a set of travelers are created, and each traveler will have an activity to be performed. For example, one traveler could be a young person going to school, another traveler can be an older person going to its workplace. Finally, there is the possibility of creating a non-random scenario by setting up all the details that characterize a real region. For example, a set of scenarios were created, one for the Principality of Monaco, one for the area around Luxembourg, and one for the ringway of Bologna. Now, there are pros and cons for each of these configuration techniques. The completely random configuration, yes, is easy to use, is quite fast, but at the same time, it provides non-realistic scenarios. The creation of a very detailed non-random scenario, on the other hand, provides a very realistic tool to study the effect of vehicular pedestrian mobility, but it requires a lot of effort, a lot of time to create configuration files with all the details regarding the region. The activity-based traffic demand generation is a good trade-off between the two. Anyway, each of the tools that are currently used in the community have their own pros and cons. ActivityGen can be very realistic, but it requires to configure a lot of details. For example, it needs to configure the density of workplaces and of residents for each edge of the map. SUMO PI is focused on the objective of the traffic assignment problem, especially for multimodal traffic. In our opinion, it's not particularly flexible, and to be used on different contexts, it requires to write code. Saga was released a few weeks ago. It's actually quite good for activity-based traffic demand generation, but in our opinion is not particularly transparent. It's not possible to apply Saga and then, before generating the routes with SUMO, to look at what actually was configured by the system, or at least it's quite hard. And that's why we are proposing random ActivityGen. Our system takes a map and it defines a number of statistical information that then are used by ActivityGen to produce the traffic demand. Those information are the location of the city center, the location and the shape of the residential areas and the industrial areas, so where people live and work, the placement of city gates, which are the connection between the simulated map and external maps that are not simulated, and the school placement. The advantages of our approach are that it's easy to use, it doesn't require much configuration, it leverages a mainstream and mature tool, which is ActivityGen, and it's also quite transparent, because the byproduct of random ActivityGen is a statistical file that then ActivityGen will use to create the traffic demand. And it's possible to inspect what was created by our tool and tune it for the particular scenario. Now, how we perform our work. The city center is computed as the average position of all the junctions. So in the end, the city center can be considered to be the body center of the city. This works with simple cities with reasonably simple shapes. The city gates are in general located far away from the center. Usually you have a city gate when you have a road that started in the map, ended outside the map, and so it was cut by NetConvert. Well, our system generates directions, and then it looks for dead ends in the different directions to find possible city gates. For the population and industry density, we use Perlin noise, which is very used in the industry in many areas. For example, Perlin noise is used to generate stains on a surface, to generate the location of trees in a forest, etc. In our case, we generate both population and industry density with it. We start by generating a Perlin noise over all the map, and then we add values to the generated noise based on the distance from the center, with the idea that the population and job densities are higher in the center of the city. And then we normalize everything to have the correct total population and correct total workplace number. By default, we define the workplace center, the industry center, as co-located with the city center, but anyway, it is possible to provide a different center for the workplace generation, while keeping the population density center in the city center. School placement. For the schools, we perform a k-means clustering of the edges to divide the edges into k clusters, which can be considered districts, and then for each district we place a school. We consider that there are three different types of schools in the area: primary schools, high schools, and colleges. We use the Danish numbers to define how many schools of each kind we want. In Denmark, in general, per 1,000 inhabitants, we have 0.2 primary schools, 0.04 high schools, and 0.015 colleges. And then, for each school that we place, we consider its type, and we set up the parameters of that school based on the type. ActivityGen requires to have for each school the student capacity, the attending age, and the opening times. And this is what we set up depending on the school type from a given range of typical numbers for Denmark. Now, let's get to the important question. What is realism for a scenario? And how do we measure the realism? We performed a long state-of-the-art analysis, and we found out that usually people either perform a visual inspection of the generated scenario, or they compute statistical measures to show the differences between two different scenarios. Usually people perform this kind of statistical analysis on a real scenario, on a random scenario, and then they prove that their method is closer to a realistic scenario. Or finally, sometimes other people applied both techniques to prove that their approach is realistic. And that's what we did. We performed a test on 5 Danish towns, Aalborg, which is the 4th largest town in Denmark, and 4 smaller towns. And we also did something in one of the scenarios tailored on a real city. For the city gates, we performed the t-test, and it confirmed that most of the times we are able to identify the real city gates in the map. For the schools, we performed an automatic assignment between real and generated schools, and we analyzed the distance between the real school and the generated one. We found out that they tend to be generated close enough to each other. Finally, regarding the population and industrial density, we performed on Luxembourg a comparison of our tool with random trips and LAST. We performed the Kolmogorov-Smirnov test, and we found out that the 3 tools produced scenarios that are statistically different. And after that, we said, okay, we don't sim the output of a totally random scenario, we don't sim reality, but are we realistic? And we performed a visual inspection on the traffic generated by SUMO from our scenario, from a scenario created with random trips, and with the last scenario. Well, we found out that the characteristics of our scenario are much more similar to last, which is reality, than to random trips. In particular, we found out that, for example, random trips doesn't create any kind of traffic jams all over the simulation, which is not realistic. In fact, we should consider that in the morning and in the late afternoon, we should have traffic jams, because there will be people, a lot of people, either going to work and to schools, and people going back home. And actually, that's what we found in our scenario. Okay, future work. In the future, we plan to apply our technique also to non-European cities, or at least non-Danish cities. We would also like to prove that our tool works at least in part in larger cities, but it will not be possible since the SUMO tools are not able to work with the bigger cities. Copenhagen is already too large for NetConvert and SUMO. And the last future work, actually present work, is the integration of our configurator into the official activity gen. In fact, the idea is to provide and integrate our code to this mainstream SUMO tool to allow people to decide to either create a pre-configuration with our tool and then the scenario with activity gen, or to just stick to the normal usage of activity gen. Thank you for your attention. I will be waiting for your questions.
Hello everyone, I'm Yang Guo from Macquarie University. Today, my presentation is about a dynamic filter demand aware vehicle dispatching system, dFDA-VeD. First, let's look at the background. The fast-growing urban population will bring more travel demand and higher pressure for the road and environment. According to the United Nations forecast, 15 years later, there will be 5.6 billion people living in urban areas. It means more than 1.2 billion people will move to the urban areas. 30 years later, there will be more than 2.3 billion people living in urban areas. To address the travel demand of the people living in urban areas, a new service, Mobility on Demand, emerged in recent years. Mobility on Demand is an innovative, user-focused approach which leverages emerging mobility services, integrated transit networks and operations, real-time data, and connected travelers. There are several companies can provide this kind of service, for example, Uber, Didi, Kairos. This kind of service has a centralized dispatching platform. First, the users or the passengers send the travel request to the centralized platform. Then the platform will match the user's request and the available vehicles by dispatching the vehicles to serve the passengers. Then there is a problem how to maximize the serving ratio for the centralized dispatching platform. Here we give the definition of our research objective, maximize serving ratio R. The serving ratio is the number of served trip requests against the total number of received requests. It's subject to several limitations. For example, number of vehicles, dynamic road graph, real-time trip request T, historical trip request H, and the passenger's maximum waiting time data. The trip request must be served in the passenger's maximum waiting time. If not, this request cannot be served. Now we give the framework of the vehicle dispatching platform. It contains two phases, online phase and offline phase. In offline phase, it used the historical data and the road graph to train a point-level demand prediction model. This model will be used in the online phase. In online phase, there are two modules. First is demand vehicle matching module. It matches the available vehicles and the received request from passengers and make dispatching. Then is the idle vehicle location module. It has three parts. First, road graph partitioning parts, then the supply-demand gap calculation parts, then the supply-demand balancing parts. The road graph partitioning parts use both the real-time attributes on vertices and the real-time attributes on edges to make the road graph partitioning. Here, the road graph partitioning is conducted in online phase, so we named our system Dynamic Future Demand Aware Vehicle Dispatching System. Compared with the traditional method, we can see on the left graph, in subgraph A, it's a static graph. It doesn't consider any dynamic attributes. Graph B is a dynamic graph. It considers the traffic information on the streets, so it has the dynamic attributes for edges. And the subgraph C is a dynamic graph with both the vertex and the edges dynamic informations. Here in our system, we focus on the graph C and consider both the dynamic demand and the dynamic traffic to get the graph partitioning results. To partition road graph, considering both traffic and demand informations, we proposed objective function to evaluate the performance of a partition. In this objective function, it combines the traffic information and the demand information. And it also has the facility for the demand information as it has an activation function. Give a toy example. Different color of the circle means different demand gaps. The red means it needs more vehicles. The blue means it has more vehicles, and the green means it's balanced between the vehicles and the demand. Then we select a true point to serve the whole area. Without considering the travel demand, the optimal solution will be circle B and circle C. With considering the travel demand, the optimal solution will be point A and point D. Here we use 5 different activation functions in the objective function. They are ignore, identify, signoid, soft plus, and real function. And we also give a location center searching algorithm. Using this algorithm, we can find the location centers in an online phase in an efficient way. In our objective function, the distance can be negative as it has an effect of the demand gap. So it is important to prove whether the algorithm can converge to a local optimal. To prove a function can converge, it should have 2 properties. First, monotonically decrease. Second, has a lower bound. Here we give the proof of these 2 properties, and by this way we can confirm that the algorithm can always converge to a local optimal. Here we give the details of our experiment. There are 4 baselines. First, integer linear programming. Second, spectral clustering. Third, power integration clustering. Fourth, dFDA-VeD system. These 4 baselines are from 4 papers, and they are listed here. The datasite we used are the New York City taxi datasite in January 2011 and the road network from Manhattan Island from OpenStreetMap. There are some setups. Passengers' maximum waiting time is 5 minutes. The number of vehicles and way changes from 2,000 to 10,000 by step 1,000. The advanced time slot T-date is 10 minutes. The future time slot is also 10 minutes. The byte time is 1 minute. There are 4 evaluation metrics. First, passenger serving ratio is the served trips against the total trips. Second, vehicle kilometers per trip kilometer. It's the ratio of vehicle kilometer VKM against the trip kilometer TKM. Third, trip kilometers per vehicle is the average trip kilometer for each vehicle. Fourth is the trip waiting time, the average trip waiting time of all served trips. Here are the results of our experiment. The subgraph A shows the served trip ratio using different algorithms for location center searching. It shows that the dFDA-VeD system achieved the best performance, especially in the peak time, for example, at 18 o'clock and around 8 or 10 o'clock. The subgraph B shows the hourly request numbers, and we can easily see which are the peak hours and which are the low demand hours. Here we give the results of all the baselines and of proposed system in all evaluation metrics. It shows that the dFDA-VeD outperform all baselines in served trip ratio, TKM per vehicle, and passengers waiting time. The difference in VKM against TKM is less than 2%. It means that our proposed system uses a very small operation cost to achieve a very big improvement. The dFDA-VeD can meet the online running requirements. The computation time for the two models are shown on the figure 7. Here we give the served trip ratio using FDA-VeD with different activation functions. It shows that the ReLU and identity achieve the best performance. However, the soft plus sigmoid perform just like ignore function. Here we show the Manhattan Island Road graph information. On the left, there are two graphs. The first shows the attributes for edges, which means the traffic conditions, and the second shows the attributes for what taxis, and it means the travel demand. On the travel demand graph, we can see that a huge number of taxis are just balanced between the demand and the vehicles. By intuition, we think that all the yellow points should be clustered into one sub-area. And figure 10 shows the partition results with different method, and it shows that only the dFDA-VeD system can achieve this. The figure 11 shows the partition results with different activation functions, and it also shows that the identity and the ReLU function can achieve this goal, and it's achieved a better performance in the serving ratio compared with other methods. Here we give the conclusion and the future work. Conclusion. First, by considering both traffic and demand to select location centers, the service quality can be improved significantly. According to our experiment results, there is only a very small operation cost increase, but it achieves a very significant improvement in the service quality. In terms of the serving ratio, the passengers' waiting time, the travel kilometers for every vehicles. The second, the activation function in the objective function matters. We explored 5 activation functions. It shows that the ReLU function and identify common function performs the best. And we also do some exploration at how to explain this result. Third, the proposed relocation center searching algorithm can meet the online running requirements. Using the proposed relocation center searching method, we can still make the idle vehicle relocation in a very efficient way. The future work. First, consider the economic effect for the dispatching platform. Second, design dispatching platform for future vehicles, for example, self-driving cars. Now, it's Q&A session. I'm more than happy to answer your question. And if you have further questions, you can also email me. Thank you.
Hello, my name is Viktor Matkovic and welcome to my paper presentation. The title of my paper is Towards Bike Type and E-Scooter Classification with Smartphone Sensors. I have many bikes and I have always felt the need to be offered different routes when I riding certain type of bike. Often I don't feel safe enough when I ride, for example, a fixie bike and the roads are full of potholes. So can we distinguish between bike types with smartphones at all to avoid those bad roads? Hence our motivation. As German survey showed that about 1/3 of all accidents without third-party involvement were caused by poor road conditions. If you're riding a fixie bike, for example, you should avoid bad roads. And for a mountain bike, you could offer a forest path to get to your destination faster. Therefore, depending on the type of bike you're riding, there are different optimal routes to improve safety and travel time. It is essential to identify the bike type so the context-based navigation system can select roads that are suitable for the current bike type or e-scooter you ride. Research on bikes in the context of ubiquitous computing is a new opportunity. Here's an example. This is a fixie bike which I mainly ride to work. In my hometown there are a lot of holes where I fell often enough because of them, and as you can see there are a lot of holes in my hometown on the roads. I have also a mountain bike, and my city also has a forest where I can reach certain destinations faster when I'm with my mountain bike. Here's an overview of the types of bike we used in the paper. At A you can see a fixie bike, which is essentially a racing type of bike. B is a city bike, which is often used in inner cities and it's very comfortable to ride. C is a typical mountain bike. This mountain bike in particular has 2 shock absorbers, one in the front, one in the back. In addition, it has very wide tires, which is ideal for riding uncomfortable road conditions, so like forest, for example, forest roads. D is a typical electric scooter. It has become very popular lately. You can find those in most cities. And it's easy to use and very nice. So we use smartphones, and in particular we use acceleration data, and smartphones also provide linear acceleration data. With linear, it usually means that the gravitational acceleration of the Earth has been taken out of the data point. The data point is usually a vector with 3 axes. Xi, and linear means also that when you're resting, so the smartphone is not in motion, the values will be about 0. And we also use rotation vectors to normalize the linear acceleration data. With this we mean removing the rotational bias. The rotational vector can be calculated by using sensor fusion algorithms, or it's sometimes or most of the times provided by the sensor itself. The sensor fusion algorithm uses acceleration magnetometer and gyroscopes to calculate the rotation vector. So the definition of the rotation vector is adhering to the definition of the Android-based rotation vector. More info on this link. The physical sensor, so the acceleration sensor, has 3 dimensions, and it's defined like this in this schematic. So the y-axis goes from bottom to top, the axis is from left to right, and the z-axis from back to front. The rotation vector represents the rotation of the device as a combination of an angle and an axis, in which the device has rotated through an angle around an axis. So in this case, an axis is here x, y, and z. Those are fixed and defined as follows. So the z-axis points to the sky, the y-axis points to the north and to the east. So the x-axis is a vector product of both y and z and points about to the east, represented as an quaternion vector, and each element in the vector is a unitless representation of the rotation. So basically, if you're using this rotation on the raw acceleration data, you get always the forces acting on the smartphone according to this definition on the axis. So Z would be always pointing to the sky, Y would always pointing to north, and X to east. I mentioned the rotation bias. So basically, if you are just using the raw acceleration data, and if you are, for example, get a force going from bottom to top, and in this rotation, for example, you would detect this force acting on the smartphone on the z-axis because it's lying flat. The same force on the same plane, basically, in this rotation of the smartphone would be detected on a sensor on the y-axis. That's the thing. When I talk about rotation bias, that's the phenomena I talk about. If you are not interested in the real-world circumstances, then you could just take the vector magnitude. So you just get the each component, so each axis, and take the magnitude. Then, so basically the length of the vector. Then you get the forces acting on all components, and basically you get the absolute acceleration, but you're losing the information about the real world. So the rotation in the current circumstances. In our case, this would be bad because if you are riding a bike, for instance, there is information about the behavior while driving also, aside from the acceleration while driving over bad surfaces. So basically, if you are riding an e-scooter, you're just standing upright and accelerate using your finger on the trigger. When you're riding a racing bike, for instance, you are like a V-wing in the X-plane and have more effort while driving. So that's also information about the bike. If you're using machine learning, there's also a problem about outliers. Specifically in this example, when you're using a gradient descent-based classification approach, then outliers can degrade your approach. This degradation is dependent on the application you want. If you just want these data points, outliers in this top corner will degrade your application because the gradient descent based on the cost function would fit your data accordingly like this. If you are clipping the data, so the outliers are removed, then you get a much better result using linear regression. So it's still dependent on the application you want. If your application should detect outliers, then this use case is still valid. So how we deal with outliers? We do not clip the data. So instead clipping the data, like I said, we are scaling the data. There are two methods basically you can do, or like 3 or 4, but the standard use case is the standard scaling method. The standard scaling method is basically remove the mean and scale according to the standard variance. So what does removing the mean mean? It's just centering the data around the 0 line and scale the distribution spread to 1. So basically every sample has the same distribution spread as through all the samples. But however, the spread and the mean is affected by the outliers. So what we instead do is instead of taking the average, we are taking the median, and instead of the standard variance, we take the range, the interquintile range. So usually it's a 75 quintile range. We are taking the 90-10 quintile range. And what it does is almost distribute the spread to 1 and almost scale to 0. So basically the data is not like shifted upwards or downwards because of the outliers. So instead we are taking the median value, which should be a normal value, which is not like too outside of the range of the sensor. So what I mean outside of the sensor, usually sensors are well defined in a range. So if we have like a light sensor, the sensor is usually well defined in a range. So outside of the range, the values can be really bad. So exponentially bad. The error is really big. And with the acceleration sensor, you have similar characteristics. For example, why do we even need to scale around 0? If you are taking linear acceleration, you should assume that you are oscillating between the 0 line. However, the sensors are not perfect, and sometimes you have a constant acceleration on the axis. It doesn't matter which axis, and this centering around 0 still is valid for linear acceleration. Same goes for the spread. You don't want the spread to be affected by the outliers, because the higher the value, the bigger the error. So we're instead of the standard variance, we're taking the quantile range. Furthermore, for our CNN, so machine learning approach, we are taking a sliding window based approach. So we have a stream of acceleration data, which then is sampled to 100 Hertz. So it's a delta between each data point to about 10 milliseconds. And we take each window is 2 seconds long, so we have 200 points. And we also do a low effort filtering by calculating the XI variance for each window, selecting the median axis variance, and using this as a threshold. So if we are then taking each window, look at the threshold, and if all xi are smaller than the threshold xi threshold vector, then it's discarded. So it's a basic low effort filtering. Our machine learning approach is based on the so-called CNN technique. CNN stands for convolutional neural network, and it works on so-called convolutions. A convolution is a matrix which is slided over the data. The matrix has weights which are randomly chosen per convolution and added together to a single value. We could show in past work that the CNN method worked the best. We compared the CNN approach with an LSTM, random forest, and perceptron classifier. And since we do not want to learn temporal features but spatial features such as acceleration behavior of a bike, the CNN worked the best. Keyword LSTM versus CNN. Here on the left side, as you can see our model. It consists of several layers. In total, we have an input layer, 4 convolution layer, 1 pooling layer, and the last layer, this one is flattened and connected with a dense neural layer of 200 neurons, which is also connected to the last 4 neurons. The connections to the last 4 neurons are dropped, so about 80% of the connections are dropped, and it is used to mitigate overfitting. The last 4 neurons represent the classes we want to classify. The softmax function, activation function, gives us the probabilities of the respective bike types to a particular sample. And for the remaining layers, we use the ReLU activation function, which is a common activation function in deep learning. The detected features of our CNN approach can be displayed with intermediate activations, so for a single sample. In this case, if you take one window and put it in the classifier, we can display each neuron as a heat map, and the higher the value, so the number is like pretty big, the higher the color. So in this case, when we take the sample and take it to the first layer, we can see there are some 2 big clusters which have high activation, so the color is really light, and the darker the color, the less relevant it is. So it's basically 0, no knowledge. So we can see that the clusters are like have most variance in the data. We can see like by eye, and in the middle there's like not so much variance, and again, at the end there's also more variance than compared in the middle. When compared to the middle. In the second layer, we can see that most of the neurons are not activated anymore. So only 2 features remain, and they have like really high activation. And also we can see there are some gaps in the data. This usually means that the features are like based on a frequency or something like this, but we can even this out to mitigate overfitting or underfitting with our pooling layer, and the pooling layer is layer 3, which blurs the features, so average is out and to the left and right, and that's why we can see that the gaps are gone. So we can conclude that the data is needed to detect features is high in variance. That's why we also filter out low effort activation windows. Yeah. For our test, we have included data from 9 different people. The data set consists of data from different smartphones, several different bikes and routes. We tested the general skill of the classifier using stratified k-fold validation. It is used to evaluate the skill of the classifier. So basically, is it overfitting or underfitting? And we use 10 folds to test this, and the results show good scores. So here you can see FlexiBike has a 0.9, City Bike has 0.92, mountain bike has a 0.88, and the e-scooter has a 0.98 score. For more information, I refer you to our paper. We also conducted a street test and weight test. So what we did basically is we took the data from person A on the route alpha and tested with person A on route beta. Same also for B. And we wanted to see if with the limited amount of training data, if we still can infer the bike types. So we still see very good results despite the small training sample. And usually with CNN approaches or complex models, small sample training sample usually results in overfitting. So it's a very good result, but despite the small training sample. We also did a weight test. So person B was equipped with additional 16 kilograms, and all bikes were correctly classified with an accuracy of 89%. And the results of this test, both street and weight tests, we can conclude that the weight and streets have minimal impact on the classifier. So if there's an impact on the classifier, it's either because of the various driving behaviors on the bikes. To conclude our paper and our presentation, we demonstrated that with the motion sensor we can distinguish between different bike types. We also introduced the term of the term subtypes in transportation mode recognition. We showed also the scale of a classifier, i.e. it's not overfitting or underfitting. We also showed that the weight of a cyclist or different road segments has no significant impact on the performance of the classifier. We also analyzed the required sampling rate, which I didn't show in this presentation, but you can read it in our paper. And for future work, we want to test more carrying positions, like a smartphone in the bag or trouser, more bikes, and first tests show good results. And yeah, I hope you liked my presentation, and I'm open for questions. Thank you.
Hello all, really honored by your attendance at our talk that presents an accurate way to predict the learning taxi fare for real-life trip trajectories via Temporal ResNet Exploration. We are the authors of this contribution, Dr. Saida Almi and Prof. Kian Lita from National University of Singapore. This is our outline. Accurate taxi fare forecasting in complex and crowded scenarios is an important building block to enable an intelligent transportation system in a smart city. Such problem is, however, not trivial, as for each trip, the fluctuation of its fare in an urban city usually follows several patterns. To address those issues, we propose a deep multi-view network called Temporal ResNet framework. Especially, our proposed model consists of 3 views. Temporal view, since the fare of a taxi trip depends on the previous time interval's fare and the time of day, such as rush hours or midnight, day or night. Special view, indeed spatially similar trip where the pickup points and the drop-off points are from adjacent road segments can have similar taxi fares. And finally, semantic view. To extract more taxi fare patterns, we integrate more factors such as trip distance, travel time, passengers count, tolls amount, tip amount, and other factors. Let's first describe the taxi market data used for modeling the taxi fare prediction problem. We have spatial data, start and end time of the trip travel time, trip distance, the number of passengers on the trip, fare amount, which is the meter fare and other amounts, and finally the total amount. The data also contains 2 other attributes like the car ID and the license ID. These 2 attributes are not considered in our study since the taxi fares are aggregated by unique trips and not taxi drivers or vehicles. The input of taxi fare prediction problem for a given trip at a given time interval t can be represented by the feature vector f that includes the time, distance, number of passengers, and all other related fare features. A sequence of the features vector f with n historical time steps can be represented as x of tr. And then the special effect can be analyzed by designing a spatiotemporal matrix X, recording the set of trips over different locations in a city and different time intervals. Our goal is to predict the total taxi fares for all trips in a trip network at a future time given the historical records over n time slots. The figure shows how the architecture of ResNet can dynamically handle the spatial dependency over time. Since the spatial dependency between locations as well as the trip's density map could change over time, features vector of trips as well as their similar trips are fed into ResNet for each time slot. To learn the spatial dynamics, ResNet uses the residual neural networks, a deeper variant of CNN, since it can effectively capture nearby and distant spatial dependencies between similar trips in a city. Based on the structure of the road network, we construct a similar trips matrix that for each trip selects a similar trip where their pickup points and or drop-off points, respectively, are located in different road segments but adjacent. Such trips may share several patterns, including the total taxi fare. After extracting the spatial patterns between similar trips, we reshape the output vector to be suitable for time series learning and feed into the bidirectional LSTM layer. In addition, the taxi fare prediction is directly affected by periodicity features. That means that taxi fares during time intervals over day may be similar on consecutive work days or weeks, repeating every 24 hours. Hence, we feed the taxi fare vectors of periodic time intervals into fully connected layers. We extract also some context factors such as events, and holidays from external datasets, feeding them into fully connected layers. And finally, by a 10-hash function, the outputs are aggregated. Here are the different parts that we describe in the following. First, we introduce how can we extract the similarity between trips and how can we learn from the spatial dependency. Then, the semantic and context features are explored. And finally, a fusion operation is employed to combine the results of each learning block. To model the structure of the road network, we refer to the graph modeling, where edges are the road segments and nodes are the intersections between road segments. We then construct an adjacent road matrix where the relation between road segments is then extracted. We add a virtual road segment for padding purpose. Let T be the set of trips TR. We use TRS and TRE to represent the start link and the end link of the trip TR. To represent the spatial similarity between trips, we use a similar trip matrix denoted by S, which records all similar trips for each trip. Three cases are shown in this figure. In all cases, trip 1 and trip 2 are spatially similar trips, since their start links or end links belong to adjacent road segments. However, in the case C, trip 3 has no similar trips. The components of the residual unit are given in the figure. This later contains three combinations of lookup operation, convolution, and batch normalization. First, we feed the matrix X into the residual block. A lookup layer is required to embed the road network topology as well as the similar trips. A stack of convolutions is used in a single residual unit to understand connections between locations with a far distance. We attempt batch normalizations after convolution layer for faster training speed. Given the taxi fare data recorded in X, the similar trips represented by the matrix S is embedded. This operation aims to perform a lookup in the embedding matrix and return the embedding of S. An embedding matrix would look like a vector of taxi fares of the similar trips in S from the fare matrix X. The tensor X at a given layer L represents the results of the lookup operation and contains not only the fare vectors of trips over n times loss, but also the fare vector of their similar trips. Note that the virtual added trip is acting as a placeholder in the lookup operation. As a second component of the residual unit, we use a 3D convolution layer to extract the features of spatial matrix. Output layer is to generate the prediction results. At an arbitrary Earth layer, we use key filters to convolve and concatenate all matrices to get X for the next layer. We use a 3D filter of dimension 1D2, where D is the column's number of adjacent road matrix A. This feature aims at emphasizing the spatial features of adjacent roads. And then to model large city-wide dependencies and connect far roads, we still need deep networks to have more consecutive layers. To address this issue, we employ residual learning in our model, and we stack several residual units. After key residual units, we use the recurrent neuron model to learn the long-term temporal patterns considering the surrounding area. On top of the key residual units, we get the output tensor where F at key is the number of the convolution filters at the last key's convolution layer, and P is the period. We then reshape the output in the way of time sequence to feed into recurrent neural network layer. we get the tensor x prime represented the road speed vectors of all n times loss. As a variant of R and N, LSTM is good at learning long time series patterns, avoiding the problem of vanishing gradient. Compared with LSTM, bidirectional LSTM utilizes additional backwards information and thus enhances the memory capability. We follow the same way to capture the temporal information of every time interval. The structure of a bidirectional LSTM can be represented by two types of connections. One going forward in time, which helps us learn from previous representations, and another going backwards in time, which helps us learn from future representations. The bidirectional LSTM layer generates an output vector yi, in which each element is calculated by using a function that combines the two output sequences. Similar to the LSTM layer, the final output of a bidirectional LSTM layer can be represented by the spatiotemporal vector YST, in which the last element is the predicted speed for the next time iteration. In addition to the spatial and temporal factors, the traffic speed prediction is affected by many complex factors such as weather conditions, holidays, and periodicity. We incorporate in our model these attributes by using one-hot encoding method to convert categorical data to a low-dimensional integer vector. Formally, a fully connected layer is adapted to extract context information and get YC for the context output. For the periodicity learning, we mainly consider three kinds of periodicity: inter-time intervals periodicity, since the traffic condition in a region is affected by recent time intervals, both near and far. Daily periodicity can be seen especially at weekdays. Weekly periodicity, for example at a certain time of Monday, the traffic speed shows a similar trend at the same time of the previous Monday on previous weeks. Using a fully connected layer, we train X, Y, XW, and XD to get YI, YW, and YD respectively. The speed prediction respecting the periodicity factor YP is obtained by the concatenation of all previous results. We merge the outputs of the first two components, we mean StackedResidual neural networks and bidirectional LSTM, with that of the external components. Finally, with a 10H function, we get the predicted value at the tth time interval. For prediction, our model can be trained by minimizing mean squared error between the predicted speed matrix and the true speed vectors. We present our experimental evaluation. We first describe the used data, then we present the evaluation matrix as well as the baselines method, and finally we discuss the experimental results. Let's begin with the description of the used datasets. The New York City road network is extracted from a public dataset and includes about 261,000 main links and 96,000 nodes. For taxi trajectory datasets, we use two real taxi trajectory datasets recorded in New York City to test our model. UIUC, New York City taxi data. It covers 4 years of taxi operations from 2010 to 2013 in New York City and includes thousands of trips. A second dataset called TLC is collected from 2009 to 2019 and contains trip information related to yellow cabs in New York City. We measure our method by root mean square error, mean absolute error, and mean absolute percent error. Our proposed model ResNet is compared with widely used traffic and fare prediction methods, which contain the traditional methods including random forest, autoregressive integrated moving average, as well as deep learning models applied on traffic and fare forecasting, such as fully connected neural networks used to predict taxi fare, recurrent neural networks used to model trip trajectories, long short-term memory used to learn to estimate the travel time, convolutional neural networks used for speed prediction in large-scale transportation network, ResNet used in StResNet model for citywide crowd flows prediction, LCRNN is a hybrid deep learning model for traffic speed prediction, and finally, STDN is also a hybrid deep learning model used to predict traffic. This figure shows the performance of the most existing models solving the traffic prediction problem. Our proposed model, ResNet, outperforms the existing approach on two real datasets, UICU datasets and TLC datasets. Details about more methods are shown in this table, where we compare ResNet model with 9 other benchmarks on real datasets. The time interval is 1 hour, and the default number of intervals to be predicted, denoted by P, is 1. We observe that our proposed ResNet model outperforms 9 well-known existing methods. Here, the figure shows the comparative performances for LSTM, CNN, StResNet, LCRNN, and our proposed model ResNet, varying the number of predicted intervals P from 1 to 4. As shown in the figure, ResNet achieves the best performance when varying P. Note that the performance becomes worse with larger P, since the correlation between fare in time intervals being predicted and fare in current moment decreases. To analyze the effect of the different components in our model, we propose 4 structures that remove the components spatial learning, temporal learning, periodicity, and context learning. Results of our evaluation without the spatial learning shows that discarding this component may reduce the accuracy achieved by our model. That means spatial trip similarity over the road network captured by our lookup layer improves the results and demonstrates the effectiveness of taking spatial dependency into consideration. On the other hand, removing the temporal learning affects the accuracy of ResNet. It is because the temporal attention mechanism is employed to select relevant hidden states of the encoder for making predictions. In addition, we can observe that periodicity and contextual learning play an important role in our approach. These additional factors boost the predictive performance, pointing out that our external extraction layer is beneficial for fare prediction. In addition to the performance evaluation, we study the computational efficiency through this figure. The results show that CNN has better computational performances on both datasets. However, in terms of accuracy, our model by far outperforms CNN approach. In addition, our approach has a better time cost than all other methods. That is because the computational cost of deep learning models essentially depends on the number of epochs used to achieve the best accuracy. The key for our computational efficiency is that our model gives its best accuracy after 30 epochs, while other testing models may require more epochs. A good trade-off between accuracy and computational cost is offered by our ResNet model. Finally, let's conclude with a small summary of what we have done. In this paper, we proposed a novel deep learning-based taxi fare prediction method that can extract spatiotemporal traffic dependencies from similar trips using a lookup layer to embed the road network and integrate it to extract spatial patterns from similar trips. The model also integrates semantic and external information such as periodicity, holidays, and weather data. We evaluate our model on 2 taxi trajectory data in New York City, achieving performances which are significantly beyond 9 existing methods, confirming that our model is applicable to the taxi fare prediction problem. Thank you all for your attention. Hello all, really honored by your attendance at our talk that presents an accurate way to predict the speed of real-life traffic data using deep stacked residual neural network and bidirectional LSTM. We are the authors of this contribution, Dr. Saida Almi and Prof. Kian Li Tan from National University of Singapore. This is our outline. Fortunately, the widest technologies have results in significant amount of trajectory which boosts traffic analysis such traffic speed prediction. This latter is of great importance to advanced traffic management systems, but challenging problem as it is affected by many complex factors such as spatial factor. We can explain that as different road segments have strong dependency with each other. For example, a congestion in a given road will affect surrounding areas, especially adjacent roads. Likewise, speed on a given road tends to slow down if congestion occurs in its surrounding area. Therefore, our proposed model extracts such spatial patterns. A second important factor is the temporal one, which has a great impact on traffic speed. For example, the speed will be much lower in the rush hours than the off-peak hours, as well as in the weekends. Thus, the traffic speed is highly correlated with the time period in a year, a month, or a day, or even rush hour or holiday. A third factor is related to the context, like some external factors, such as driver profile, traffic lights, events, and weather conditions. In the following, the components and the architecture of the proposed model are described in detail. But we first give out the formulation of the network-based traffic speed prediction. A vehicle speed and position at a certain time can be provided by a recorded vehicle trajectory. For each road segment, we compute the average traffic speed from the GPS pings. At one location, our input can be represented by the vector xt, which is a sequence of speed values x with n historical time steps. But the traffic speed at one location can be impacted by nearby and faraway locations. For this reason, we design a spatiotemporal matrix recording the speed of all road networks over n time slots. As shown in this figure, the architecture of our model contains 4 major components, which are several residual layers to model the spatial evolution, then a recurrent layer, and more specifically we use the bidirectional LSTM component to model the temporal dependency. And then a periodicity extraction layer, and finally a context extraction layer modeling the external influence such as weather and holidays. For learning spatial patterns, our model employs residual units since it has very deep structure that can effectively capture the spatial traffic dynamics from nearby and distant regions. After extracting the special patterns, we reshaped these features to be suitable for time series learning and feed into the RNN layer, and more specifically a bidirectional LSTM as a deeper variant of RNN for sequence modeling. In addition to that, the traffic speed prediction is directly affected by periodicity features. For instance, a traffic congestion occurring at 8 a.m. will be almost the same as tomorrow at 8 a.m. also. It means that traffic conditions during morning rush hours may be similar on consecutive work days or weeks, repeating every 24 hours. Hence, we feed the speed vectors of periodic time intervals into fully connected layers, FC. For the external learning, we extract context factors such as weather, event, holidays, and so on from external datasets, feeding them into fully connected layers. By a 10-hash function, the outputs are then aggregated. To model the structure of the road network, we refer to the graph modeling, where edges are the road segments and nodes are the intersections between road segments. We then construct an adjacent road matrix where the relation between road segments is then extracted. We add a virtual road segment for padding purpose. The components of the residual unit are given in the figure. This later contains three combinations of lookup operation, convolution, and batch normalization. First, we feed the speed matrix XRT into the residual block. A lookup layer is required to embed the road network topology. A stack of convolutions is used in a single residual unit to understand connections between locations with a far distance. We attack batch normalization after convolution layer for faster training speed. Given the traffic speed data recorded in XRT, the topology of road network represented by the adjacent road matrix A is embedded. This operation aims to perform a lookup in the embedding matrix and returns the embedding of A. An embedding matrix would look like a vector of speed values of the adjacent roads in A from the speed matrix XRT. X at a given layer, L, represents the result of the lookup operation and contains not only the speed values of R rows over N times loads, but also the speed values of their adjacent roads. Then we have note that the virtual added road is acting as a placeholder in the lookup operation. As a second component of the residual unit, we use a 3D convolution layer to extract the features of special matrix. Output layer is to generate the prediction results. At an arbitrary health layer, we use key filters to convolve and concatenate all matrices to get X for the next layer. We use a 3D filter of dimension 1D2, where D is the column's number of adjacent road matrix A. This feature aims at emphasizing the special features of adjacent roads. And then to model large city-wide dependencies and connect far roads, we still need deep networks to have more consecutive layers. To address this issue, we employ residual learning in our model, and we stack several residual units. After key residual units, we use the recurrent neuron model to learn the long-term temporal patterns considering the surrounding area. On top of the key residual units, we get the output tensor where f at key is the number of the convolution filters at the last key's convolution layer, and p is the period. We then reshape the output in the way of time sequence to feed into recurrent neural network layer. We get the tensor x prime represented the road speed vectors of all n times loss. As a variant of R and N, LSTM is good at learning long time series patterns, avoiding the problem of vanishing gradient. Compared with LSTM, bidirectional LSTM utilizes additional backwards information and thus enhances the memory capability. We follow the same way to capture the temporal information of every time interval. The structure of a bidirectional LSTM can be represented by two types of connections. One going forward in time, which helps us learn from previous representations, and another going backwards in time, which helps us learn from future representations. The bidirectional LSTM layer generates an output vector yi, in which each element is calculated by using a function that combines the two output sequences. Similar to the LSTM layer, the final output of a bidirectional LSTM layer can be represented by the spatiotemporal vector yst, in which the last element is the predicted speed for the next time iteration. In addition to the spatial and temporal factors, the traffic speed prediction is affected by many complex factors such as weather conditions, holidays, and periodicity. We incorporate in our model these attributes by using one-hot encoding method to convert categorical data to a low-dimensional integer vector. Formally, a fully connected layer is adapted to extract context information and get YC for the context output. For the periodicity learning, we mainly consider three kinds of periodicity. Inter-time intervals periodicity, since the traffic condition in a region is affected by recent time intervals, both near and far. Daily periodicity can be seen especially at weekdays. Weekly periodicity, for example, at a certain time of Monday, the traffic speed shows a similar trend at the same time of the previous Monday on previous weeks. Using a fully connected layer, we train X, Y, XW, and XD to get YI, YW, and YD respectively. The speed prediction respecting the periodicity factor YP is obtained by the concatenation of all previous results. We merge the outputs of the first two components, we mean StackedResidual neural networks and bidirectional LSTM, with that of the external components. Finally, with a 10H function, we get the predicted value at the tth time interval. For prediction, our model can be trained by minimizing mean squared error between the predicted speed matrix and the true speed vectors. In the following, we present our experimental evaluation. We first describe the used data, then we present the baseline methods, and finally we discuss the experimental results. For the dataset, we have used two real taxi trajectory datasets. The first one is a public dataset on which we extract special features and conduct our following experiments. This dataset covers 700 million taxi trips from 2010 to 2013 in New York City. It contains accurate hourly average traffic speed measurement for almost all road segments of the New York City road networks. The road network includes about 261,000 main links and 96,000 nodes. Only holidays information are used for the context learning. Among the data of the year 2013, 3 months data are used for evaluating the model, and the last 3 weeks are for testing. A second dataset is collected from taxi trajectories in Singapore from 1st December from 1st December to the end of this month. We mainly extracted a graph containing 74,000 main rows and 273,000 nodes. Our baselines includes 9 methods. The support vector regression is a powerful regression method. The autoregressive integrated moving average is a well-known model for predicting future values in a time series. A recurrent neural network is a method to temporal sequence values. Gated recurrent unit is an improved version of standard recurrent neural network to keep information from long ago without washing it through time or remove information which is irrelevant to the prediction. Long short-term memory, LSTM, were developed to deal with the vanishing grading problems that can be encountered when training traditional RNN. Convolution neural network uses convolution, pooling, and fully connected layers to predict traffic speed. StResNet, it uses residual network to model 3 temporal properties for traffic prediction. And finally, LCRNN, it uses convolution, RNN, and fully connected layers for speed prediction. We measure our method by root mean square error, mean absolute error, and mean absolute % error. Here we can see how our model did over time, let's say 10 epochs. First, we show accuracy behavior on training and validation set. Interestingly enough, our validation accuracy still continued to hold. Then we show the shape of training and validation loss respectively. Loss is the measure of error. The lower the loss, the better a model. It clearly looks that validation loss is improving over epochs. First, we compare our model with 9 other benchmarks using 2 real datasets collected from Singapore and New York City. The time interval is 50 minutes and the default number of intervals to be predicted is 2. We observe that our proposed model is better than 9 benchmarks. It outperforms 9 well-known existing methods. In addition, to analyze the effect of the different components in our model, we propose 3 structures that remove the components periodicity learning, context learning, and spatial learning, respectively. Results of BioNet without the lookup operation shows that discarding this operation or the lookup layer may reduce the accuracy achieved by BioNet. That means the topology of road network captured by our lookup layer improves the results and demonstrates the effectiveness of taking spatial dependency into consideration. In addition to that, comparing BioNet to BioNet without periodicity and context extraction layers, we can observe that the results is further promoted using periodicity and context learning components, respectively, pointing out that external extraction layer is beneficial for speed prediction. Let's now see the effect of the number of predicted intervals in the future denoted by P. The default parameter P is 2. These 2 figures show the comparative performances for LSTM, CNN, StResNet, and BioNet, varying the number of predicted intervals from 1 to 4. As shown in the figures, BioNet achieves the best performance when varying P. Note that the performance becomes worse with larger P, since the correlation between speed in time intervals being predicted and speed in current moment decreases. Here we analyze the traffic pattern at different scenarios during the test period in the last week of December. This figure shows the model performance on different road types randomly chosen, mainly 3 types such as motorways, residential ways, and trunkways. These observations were on different days, both weekdays and weekends. The days in the figures are in chronological order from 25 to 31 of December. The accuracy of our model over different road types in the difference between predicted speed values and real values. We use 10 epochs for training the model. On different road types, the BioNet model has a good performance on Tuesday, 25th December, which shows our model capacity to learn special patterns on holidays. For residential and trunk roads, the accuracy value slightly increases over weekdays, but decreases on Saturday and Sunday, which shows that our model is good at learning temporal patterns in both residential and trunk roads. For motorways, our model has shown a similar behavior, and the accuracy value slightly increases and decreases over days. Finally, let's conclude with a small summary of what we have done in this paper. Indeed, we have proposed a novel deep learning-based traffic speed prediction method that can extract spatiotemporal traffic features using a lookup layer to embed the road network and learn surrounding areas dynamics. The model also integrates external information such as periodicity, holidays, and weather data. We evaluated our model on 2 road networks in Singapore as well as in New York City, achieving performances which are significantly beyond 9 existing methods, confirming that our model is applicable to the traffic speed prediction problem. Thank you all for your attention.
Hello everyone, my name is Rui Henriques and today I'll be presenting to you our work on the discovery of emerging patterns from spatiotemporal data produced by heterogeneous sensor networks. This work was developed by Francisco Neves and Ana Fina Amor under my supervision. So let us start right away with the motivation for this important problem. Then we will introduce the proposed solution, the two-path approach. Finally, we will check the results on some real sensor networks. And finally, we will be presenting the major concluding remarks. So all of us are familiar with heterogeneous sensor networks. For instance, if you consider water supply systems, we may have sensors associated to measure the water quality, flow, pressure. Or if we look to urban systems, we have, for instance, road traffic monitoring systems, where we can have both mobile and stationary sensors. So the mobile sensors usually correspond to geolocalized speed data. So the sensors are our mobile devices that measure our trajectories. And the fixed sensors correspond to, for instance, inductive loop counters that measure the number of cars passing at a given location. So when we look to these networks or others such as communication networks, body sensor networks, it is very important to detect events of interest. And a specific event of interest is an emerging behavior, something that is changing within the system. For instance, when we look to communication networks, we may be interested in understanding specific paths that have an increasing congestion in terms of traffic. It may not be that bad, but it's increasing. So it's denoting that some problem might be observed in a future. Okay, so the timely, robust and timely identification of this upcoming bottlenecks is very important. And so why the detection of these emerging behaviors is challenging? As I said, the behavior is changing but might not yet denote a bottleneck. Also, the data produced by these heterogeneous sensors has complex spatiotemporal idiosyncrasies. And also, if we look, for instance, to urban systems, we may have thousands and thousands sensors producing massive signals during long time periods. So our quest here is to discover emerging patterns in an effective and highly scalable way, dealing with those all spatiotemporal complexities. Okay, once we have such an approach where we can apply it for different types of systems, so body sensor systems, utility supply systems, communication systems, urban systems. I gave previously the example of mobility systems, and all of us are aware of the impact that those congestions have in our daily lives and also on the environment. In fact, we not only develop our ETUPAT approach, but we validate it on a real sensor network, a road traffic monitoring system using Lisbon as our study case. Okay? In fact, our contributions were developed in the context of a research project called ILU, Integrative Learning from Urban Data. There is a partnership here in Portugal between some research institutes and the Lisbon City Council and some public carriers. This is a large-scale network of sensors, thousands and thousands of mobile sensors that correspond to the geolocalized speed data, and here our provider is Waze, as well as many stationary or fixed sensors that correspond to the inductive loop counters. Okay? And here our goal is to discover traffic patterns of road mobility, so those congestion or decongestion patterns that may denote upcoming problems. Okay, but this is not as simple as you may thought, because here we want to combine the views produced by these different sensors. So we want to look to speed limits, the flow of vehicles, the extension of our road congestions, as well as guarantee the statistical significance, actionability, and interpretability of the emerging patterns in order to translate these outputs in meaningful mobility reforms. So our first question would be, okay, is there anything available in terms of related work? Yes, so there are contributions available from two major research streams: time series data analysis. So in this context, the notion of a nonlinear trend exists for a few decades. And for the community of machine learning, especially those working on pattern mining, there's also a similar concept, also referred as growth pattern discovery or changing pattern discovery, that in fact is not so similar because it corresponds to how patterns change between two data sets, where each data set corresponds to a different point in time. Okay? Although those contributions are very relevant, they do not address some of the challenges that we want to satisfy here. Okay? We have this high scalability need, so efficiency requirement. We also need to handle spatial and calendrical aspects. Okay, for instance, if we are looking to congestion patterns, we know that traffic patterns differ between a Monday and a Tuesday, or a weekend or a holiday, and also when we are looking to on versus off academic periods, okay, traffic patterns vary a lot. So we have here spatial and calendrical temporal context that we cannot simply neglect, okay? And we also want to deal with this heterogeneous data produced from heterogeneous sensors. Okay, so we need to go ahead. And for this, we propose the two-path approach. So the two-path approach is composed by two major components. Okay, one component that is responsible to map our raw spatiotemporal data structures into more conducive data structures, and on our second component handles the discovery of emerging patterns. Okay, so much of the complexity is on this first component because, as you may guess, when we are working, for instance, with geolocalized speed data, where each event is annotated with a specific trajectory and measures different aspects such as speed limit, etc., etc., we need to have a good data mapping in order to not lose important information, while still handling the different spatiotemporal data structures that are produced from the different sensors. So here, one thing that is important is to clearly understand what are spatial, temporal, and calendrical constraints. Since events are usually annotated with a trajectory, we need to have very well-defined spatial criteria. So for this purpose, we segment roads using a fine granularity. The same with time. We also establish a fine time granularity for the discovery of the emerging patterns. And regarding the calendrical events, although we give the user the freedom to define what kind of calendars does he need, we also provide default calendars for the discovery of the emerging patterns. Okay, here we were thinking in terms of the seasonality aspects. So we are considering, for instance, as calendars each day of the week, weekdays, holidays, and all these different options for both on academic and off academic periods. Okay, so all the details regarding these complex data mappings from our raw spatiotemporal data structures into more conducive data structures, which are in fact multivariate time series data structures, are described in detail in the paper. Okay, so once we have our multivariate time series data, now we can discover our emerging patterns using very simplistic yet effective differencing, regression, and scoring operations. Okay? Okay, so what is the differencing operation? Simply subtracting the values between two consecutive time points. And why we are doing that? Because we do not only want to find linear trends, but as well non-linear trends. So here is an example of a time series before and after differencing operation. So this non-linear exponential trend becomes a linear trend when looking to the differentiated space. So we can even apply more than one differencing operations on a given time series if we want to detect abruptly changing patterns. And the interesting thing is that we can apply this isolatedly for each time series and within each time series to each variable of our multivariate time series dataset in order to detect thousands or millions of emerging patterns. So then our next quest is to evaluate how relevant is each one of those emerging behaviors and then combine them into a meaningful set of emerging patterns that can be easily interpreted to the user. Okay, so then the question becomes, how do I assess the relevance of each one of those emerging behaviors? Okay, and for this we propose an integrative scoring that combines a multiplicity of criteria of interest and yields very interesting statistical properties. Okay, so first of all, we want to detect these different emerging profiles, linear and non-linear profiles. We want those profiles that are, for instance, exponential to be more relevant than those that are simply linear trends. Okay, not only because of those non-linear are sometimes less trivial to detect, but because they may denote a higher degree of complications in the future. Okay? The growth rate associated with those emerging profiles is also an important indicator of the relevance of the emerging behavior, as well as how well am I fitting this profile. And finally, the recurrence. For instance, if I'm looking to a pattern that is emerging along some Mondays, that is certainly different than a pattern that is emerging based on all Mondays from my data set. Okay? So this integrative scoring yields, as I said, many properties of interest. One is that it controls the false positive and false negative rate. How? What is, by the way, what is a true positive? Is an emerging pattern that was detected. Okay? And so what is a false positive? Is something that was detected yet is not an emerging pattern. Okay? And what is a false negative? Is an emerging pattern that was not recovered by. Okay? So having this integrative scoring, measuring those different properties and combining into a meaningful score guarantees a minimized predisposition to these false discoveries. Okay? Also, the score is bounded between -1 and 1, where -1 reveals descending emerging profiles and the 1 highly ascending emerging profiles. Okay? Also, the values of the scores are normally distributed. They pass the test of normality. So they have higher probability of have a value of 0. Okay? So this is also important if we want to statistically test those patterns in order, for instance, to obtain a p-value. And finally, this score is very easy to interpret what's going on. How relevant is a given pattern? So let us right away check some of the results from the application of Etupad on our case study, road traffic monitoring system in the city of Lisbon. Okay, so here on this table, you can see a set of emerging patterns that were detected by the Etupad approach. Okay, so on the top we have the congestion patterns, the more relevant ones, and on the bottom part we have the decongestion patterns. Okay, so we can here see the time of the day where that pattern is observed. We also have information pertaining to the calendar. Here we have also the location, the traffic view, whether it's speed limit, the extension of the jam, or the traffic, the car frequency, the profile, whether it's emerging or an abrupt change, and the integrative score. And we also disclose the values of each one of the criteria that is used by the integrative score. So a mobility expert can look to this table and right away assess some of these emerging behaviors that are happening in the city. Okay, here is just a zoom on 4 of those emerging patterns, okay, for illustrative cases here. Probably you do not want to do the calculus of the integrative score because we provide Etupad as a software tool, and we have the link available in our manuscript. It's available via GitHub, okay? But if you are curious to understand how the integrative score is computed, here we provide some examples. These 2 top patterns are in fact nonlinear trends. These details were produced after the differencing operation. Okay, so we provide our E2PAT approach within a highly usable software tool, okay, using a graphical user interface with different visualization facilities. So in this slide, you can see here on the left part some of the parameters that are accepted in our software tool. So for instance, here the user can specify. Remember when we talk about data mappings, I was referring to the spatial, temporal, and calendrical constraints. Here the user can specify those and select some sensors. He may only be interested in a specific part of the system. And here on the right side, we have some examples of the outputs that are produced, specifically the visualization of the congestion and decongestion patterns in our road traffic monitoring system at Lisbon. So here the road segments are colored in accordance with the emerging profile and its severity. Okay, so here are our major concluding remarks. So E2PAT is an approach able to discover emerging patterns from networks of heterogeneous sensors. Okay? One thing that I did not refer is that our E2PAT approach is able to discover these patterns in linear time. Okay? And the computational complexity of E2PAT is shown in our. Okay, we can detect different emerging profiles and be able to handle the spatiotemporal complexities associated with the data produced by these different types of sensors. And we also allow E2PAT to run without the user worrying about spatial and calendrical constraints. Although the user can still input them, E2PAT has flexible default behavior in order to handle this. Okay, we also show how can we measure the relevance of these patterns using a novel integrative scoring that yields statistical properties of interest, and we also provide E2PAT within software tool with visualization facilities in order to guarantee the usability of the pattern analysis process. So thank you for your attention, and now questions.
Hello, my name is Diogo Lima. I am a PhD student from the University of Lisbon, and I'm presenting my paper called State Deployment in Fog Computing. Nowadays, we have an increasing number of large-scale mobile distributed applications that mediate the interaction among a vast number of users and manage the shared objects, the application state that users can either read or write. Examples of such applications include vehicle sharing applications, multi-user games, or social networks. And the current trend is to centralize all the application state that can be manipulated in the cloud. However, this imposes a geographical barrier between the end users and the application state, as the latency and jitter that results from that distance negatively impacts application performance. Fog computing tries to address this issue by deploying surrogate servers at the edge of the network, in places such as bus terminals, shopping malls, or public services, bringing the application state closer to the end users. This model has the potential to mitigate jitter and end-to-end communication latency, but its effectiveness strongly depends on being able to deploy each application state component at its most convenient location. For example, on the right-hand side, we show the hashtag utilization of the 4 of the 4 largest cities in Portugal. And we can clearly see that some state is more frequently used in one location than in the other. Now, it is important to notice that fog computing is different than content delivery networks. Even if they are both focused on reducing latency by approximating data to the end users, in fog computing that data can be manipulated and even new content can be created. And among that data, we may also find different characteristics. For example, we may have steady data that is mainly relevant in a location, such as a specific landmark in a city, or mobile data that must follow the user, such as his personal settings or daily agenda. So when devising deployment strategies, we are faced with the following challenges. First of all, we need to anticipate future utilization patterns. And also, we need to be able to identify cross dependencies among data. And also, we want our strategies to be application independent. So, to be completely oblivious of application semantics. Based on this, each state deployment decision must consider the cost of migrating itself with the possible benefits that it brings to the system performance. To evaluate our geo-deployment solutions, we focused on 3 metrics. The first one is the time required to complete transaction duration. Then we focused on the number of local transactions. The better the deployment strategy and the deployment of data is, then the number of local transactions will increase. And finally, the number of migrations performed, because they also represent a penalty to the system. So our goal, the goal of deployment strategies, is to minimize performance, minimize duration as a way to improve performance. And by minimizing duration, subsequently will be increased local transactions, and if possible, try to minimize the number of state items migration, as it must bring disturbance to the system. Based on that, we propose and follow different deployment strategies that fall into 3 categories. The first one we call linear approaches that rely on simple, intuitive data structures. The first one, and the baseline test, is called static, where each state item is permanently assigned to the surrogate where it first used. And no migrations are performed. Then we have aggressive polling, AP, where objects are moved to the surrogate that presents the higher utilization count. And finally, DSSMR, which is based on the strategy presented for dynamic state machine replication in a paper, the DSCN 2016, that moves all objects to a single surrogate prior to transaction execution. The second class of strategies rely on latency, as we believe that latency is the main element and is the most recent and trustworthy metric that we can obtain from the system. In this sense, latency replacement compares the impact of keeping an object in a current location against moving it to a new surrogate. It calculates the average duration time of transactions with the object in the current surrogate, with the estimated average time if the object was stored on another surrogate, and chooses the minimum. The polling and latency strategy, so P plus L, tries to go a step forward and apply a different strategy depending on the type of application state being considered. We referred earlier that some components of the application state can present different utilization patterns, such as steady data and mobile data. And by relying on annotations that programmers can provide such hints without the algorithm knowing the application semantics, but by providing annotations over the data, it's possible to use the PL approach and applying the polling approach of the highest utilization count to steady data or to data marked as steady data, and relying on the latency replacement approach to find the best deployment of data annotated as mobile data. Finally, the third class of strategies formulates the problem of geo-deployment as a genetic algorithm, where each object and its location represents a gene, genes that can be mutated and varied in order to find the best population, which in this case is the best deployment for each object, according to a feed function. Our feed function consists yet again in minimizing the sum of transaction durations. Now, to evaluate all these approaches, we use the Austin V-Cycle application. Austin V-Cycle is a publicly available bicycle sharing service from the city of Austin in the United States, where users can check out and return bicycles to specific stations called kiosks. On the right-hand side, you can see the kiosks distribution around the city area. So we collected bicycle trips from a 2-year period, collecting data from 513 bicycles and 96 kiosks, and mapped those bicycle trips onto transactions to create 2 workloads, each with around 100,000 transactions. In the first one, called multi-object, 90% of the transactions have 3 or more objects, with users checking out the bicycle from one kiosk and reserving a parking slot at the destination, or by probing various kiosks on a 500-meter radius for available bicycles and then check out the bicycle. In the other workload, called localized, 90% of transactions have exactly 2 objects: check out the bicycle from a kiosk or return it. To perform the evaluation, we divided the city of Austin into 4 areas, each with 1 surrogate to store bicycle and kiosk data. To emulate the geographical distance between surrogates, we deployed those surrogates in Amazon instances in different data centers. And a transaction issued by a surrogate represents a request from a nearby client. In the meantime, an oracle running each algorithm is at the background in the cloud, collecting transaction logs from the surrogates and periodically reevaluates the state deployment at each 10,000 transactions observed. So what results did we obtain? Let's take into consideration our main objective, reduce transaction duration. And let's first focus on the multi-object workload. We can identify 3 categories of algorithms. First of all, static, the baseline test, which increases a long time, meaning that the initial deployment becomes more and more outdated with the evolution of application usage. Surprisingly, the SSMR, the approach that pulls all objects to a single surrogate before executing it, shows similar results to static, meaning its eagerness is being counterproductive. Improving from the results are the polling and latency approaches, especially AP presents better results than a latency sensitive LR, meaning that a polling strategy is useful to at least some objects. And when combining polling with latency in polling in P plus L, benefits even more the system, as it is a strategy that presents the lowest transaction duration. On the opposite side, the genetic algorithms present the worst results, even surpassing the baseline test, proving that is taking the wrong decisions. In the localized workload, some behaviors are maintained and others appear. For example, the genetic algorithms present once again an initial spike different from anyone else, but is now able at least to conversion and ends up outperforming the baseline test. On the other side, the SSMR now presents the best results, consistently improving transaction duration, benefiting from the fact that its eagerness in a workload that presents a lower degree of data correlation, because most of the transactions only have two objects. Its eagerness is benefited in such scenario. Finally, polling and latency approaches appear in the middle, still able to cut transaction duration by half when compared to static. And of the three, P plus L is once again slightly better. To complete this analysis, we focus our attention to the cumulative distributed function of transaction times of the localized workload. And here the best results are obtained at the top left corner, meaning that more transactions are taking less time to complete. It is interesting to observe the SMR in this figure. We can see that 60% of transactions are local transactions. However, we can observe the impact of when the SSMR really needs to cope with transactions involving multiple surrogates, because it's pulling the objects to a single one prior to transaction execution, his performance is significantly hampered. On the other side, P plus L appears once again at the most left-hand side, showing it's outperforming its peers. And also the SSMR, but when having more data correlation per transaction, so these longer transactions also explain the results obtained in the multi-object workload. In terms of migrations, we can see that the aggressive polling performs less migrations than the others. Please note that static is not present in each figure because no transactions are performed. And the SSMR, since it performs migrations on a per transaction basis, results are not comparable. So by presenting in benefits in terms of transaction duration and a low amount of migrations, we can conclude that aggressive polling is actually taking good decisions. The latency sensitive approaches, LR and P plus L, present more migrations. Still, they are all around 10% of the data set migrated per evaluation window, which is not a significant overhead, but they perform more transactions. But by observing that P plus L even outperforms AP, this proves that the overhead in migrations are actually correct decisions that must be performed because they benefit the system. From all these algorithms, genetic algorithms is the one that performs more transactions, around 10% of data set migrated per evaluation window. But when compared to the transaction durations obtained, clearly these decisions are not the correct ones. So in conclusion, we have shown that algorithms have sensibility to different workloads and this impacts performance. For example, the SSMR is the best example, as it's tailored to transactions with a small amount of objects per transaction, and that its eagerness backfires in workloads with different characteristics, especially with higher degrees of data correlation and multi-objects per transaction. Genetic algorithms presents itself worse than the baseline test static. and even performing migrations. And the problem is that compared to all the other algorithms, which take about 500 milliseconds to output a decision, the genetic algorithm takes about 5 to 6 minutes, which means that actually, though those decisions are not incorrect, the problem is that when the algorithm finally outputs a decision and applies them, they do not represent the reality. And so the decisions are always chasing after the application, and the deployment, it's never the correct one. And that's hampering the system. Finally, latency and polling approaches are shown to be more adaptive. And in particular, P plus L, which combines both depending on the data characteristics, has shown the lower transaction durations on average. And the fact that exploiting these different types of objects is improving the system. And actually, even if it makes more migrations, at least they are the correct ones and should be performed to improve system performance. That's all. Thank you very much. Now I'll take any questions you may have.
Hello, dear organizers and participants of this conference. I am Abagaz Muhammad Said. I am from University of Electronic Science and Technology of China. It's really a great honor for me to participating in this international conference. I present on behalf of other co-authors. Our title is Multi-Agent Rail-Based Computation, Offloading, and Resource Allocation in UAV-enabled IoT Edge Network. There is outline, introduction, system model, multi-agent rail-based computation, offloading, and resource allocation, simulation results, and conclusion. The first part, introduction, include context, significance of the work, and contribution. In the context, there is a resource allocation and computation offloading scheme in emergency communication. That means when the base station will be failed or overloaded, or IoT device is far from the network. So how can we solve the problem in resource allocation and computation offloading? So a resource allocation, it is transmission power and computation a resource, we call it CPU, allocating proper resource, proper association between IoT device and computational node, either it is real base station or base station, efficient resource utilization to ensure quality of service. In computation offloading, there is multitask and multiple IoT device and computational nodes. IoT device offloaded computation intensive task into base station or real base station take at the station by itself to ensuring quality of service. Different computational node providing different service with ensure quality of service and reasonable resource demands. Those real base station we deploy a real base station to serve the ground network when the emergency is existed, to relay information or allocate a resource to IoT device. The significance of the work: many workers have investigated computation offloading and resource allocation in IoT edge network with integrated of UAV network, most of them using single agent or heuristic algorithm. Here, the following questions have still not been answered in UAV-enabled IoT edge network in emergency scenario. The first one is, how can we ensure the quality of service of IoT devices when the local base station with edge server overloaded, malfunctioning what existed, and the IoT device far from the network coverage? The second question is, how can we obtain optimal offloading policy and efficient resource allocation for IoT device with limited competition and transmission power resource available and emergency was existing in a high dynamic environment where offload offloading and resource demand change in real time, how can the resource allocation scheme intelligently respond to varying nature of the network and adapt to the change? Then our motivation is on this paper develop a multi-agent DRL-based scheme for computation offloading and resource allocation. The objective is to minimize system costs in terms of energy consumption and time delay to ensure quality of service of IoT device by deployed UAV network. Our contribution is to propose a multi-agent DRL-based computation offloading and resource allocation framework in aerial to ground network. Area to ground network, when the device or the IoT device offloading task into computational node when the task is over their own computation capacity, and if the low power existed on the device, so they couldn't process the task. So to solve this problem, the task must be offloaded into the nearest base station or aerial base station. So our simulation are conducted to verify the performance of proposed framework. The results are compared to single agent, DDPG, and dual-link QN and QN scheme. System model focus on computational model and energy model. Here is the system model. In this system model, there is a controller, network controller that controls the integration of UAV network and IoT edge network. In the UAV network, there is clustered UAV that managed by UAV head, and this cluster is swarming over a ground network. And this one is a small cells. It has ultra dense heterogeneous device, and there is another device is far from this cell that is suffer to accessing the network. So by this reason, the UAV can assist the device or enable the network. And these two base stations, whether it is failed or overloaded, so the UAV network can serve this network by serving different services like allocate resource or relay information into a controller or MEC server. So when the task offload from IoT device to any computational node, there is uplink array, so we can calculate by this equation. And during offloading the task, it has two sub-channel status, whether it is available or disconnected. So we can represent by this value, whether it is 0, it is disconnected, 1, it is available. So the aerial to ground communication link are modeled by a probabilistic path laws model containing the line of sight and null line of sight in different probability of occurrence. So this line of path laws mode is depend on environment and network. So computational model is a computational model. Any task, any IoT task, it has three profiles. The first one is size of the input, required computation. The second required computation capacity, that process input task, and maximum time delay. So when the task is processed on local device, it has their own time delay and energy consumption. If the task is out of the capacity of the IoT device or the local device, it must be offloaded into the nearest base station. So we use computation offloading decision parameter alpha L x m t is equal to -1, 0, and 1. If it is -1, the task offloading into UAV network, and 0, the task compute all locally. 1, the task offloading onto the base station. So to prevent inter-cell interference, we define single signal to interference plus noise ratio. So when the task, the IoT device associated with base station in the normal station, it has their own SNR value and actual data rate and transmission delay cost. So we can calculate using this equation. So when the task also offload into base station, aerial base station, it has the same as the base station, but the difference is some calculation is different from base station. So this del ut less than or equal to h ut tan theta u, it is UAV network coverage range. And it has also transmission delay, task execution delay at UAV network. So totally, the total delay cost of task execution on computational node X is the transition time and execution time, sum of this time. So we can go to the delay cost. The energy model in energy, especially transmission power, it is a continuous variable. To handle this, we change into discretize a value or into vector value. So each task or each IoT device may compute their task locally or offload. At this time, it has their own time energy consumption when it compute locally or offload into any computation node. So when it is offload into any computation node, there is transmission power and energy consumption to execute the tasks. So it has two power consumption, but when using UAV, it has flying the power consumption and hovering time consumption, but we focus only transmission and execution time consumption. And the computation resource has also their own constraint. Compute any task, the computation capacity must be less than or equal to the maximum value. So to handle this dynamic and continuous action space, we use a multi-agent DRL scheme. The multi-agent DRL scheme that train in decentralized centralization and execute decentralized manner and supports cooperative of agents. So this approach agent have actor critic network, this centralized execution and a critic function in centralized training part. The centralized training critic function or action value function when we use multi-agent deterministic policy gradient method. This is one of multi-agent DRL scheme. So this one is used to handle the continuous action space, and this one is model-free DRL method. So our target is to minimize the energy and the total energy consumption and time consumption. This is the sum of two, and all of the energy consumption and time consumption has their own weight index. Here is the framework. In this framework, each IoT device, or we call it as agent, has their own state and reward and generates their own action, because the decision is independent and the agents share information from another agent. At this time, they can minimize the communication cost and so on. So one agent associates with one computation node at time t. So as finally, we take the aggregation or the join of action on base station and on action, and we can take all of them in one. So we take a state as task profile and UAV network status. It indicates resource and coverage as SINR of both base station and UAV. That means SNR between the agent and computational node. And the other one is task type, either delay sensitive or delay insensitive task. This is as a state in the DRL. So action, in the action, each agent make a decision independently. So it has three parameters of action. One is selecting the computational node, this one, and selecting selecting computational resource and transition power by this volume. So the reward is to ensuring quality of service in aerial to ground network. We design a reward function which minimize overall computation costs of tasks in different computation node at time slot team. So the reward is we calculate reward of energy and reward of time. So the reward of energy of agent L calculated by the difference energy or energy consumption local and the energy consumption when task offload into base station or UAV. The time also the difference between local time delay and task when task offload into base station or UAV, there is a time delay, so we can subtract from the local. So the overall reward of all agent at time slot can calculate by this equation. So the main target is minimize the computation cost in aerial to ground network. This pi asterisk is equal to arg mean expected pi t stars 1 up to positive infinity lambda t minus 1 RT. Then this is as the main target to minimize the computation cost. In the simulation result, we use this different parameters and the value by using this parameter to test whether our proposed method is achieved or outperformed than other baseline algorithm. So we use these parameters. So we compare our proposed method with single agent DRL, this DTPG, dualing DKWN scheme. Here is the output when we use epoch training, epoch and numerical average cost. So the first one is when the agent access only the base station, when action selection policy is one, that the agent access only the base station. Maybe it is overloaded or it is damaged or it's normal, but at this time the cost is high, but the multi-agent it is better than the single agent. Here when the computation node base station and aerial base station, this one is better than this because the action selection is equal to 0.5. That means the agent can access the agent is opportunistic, can access the aerial base station and the base station. But if the base station overloaded, so the agents can offload their own task into aerial base station. This one is better than the first one. And this in both situation, the multi-agent output is better than the single agent output. So here the compared to numerical value of power and time respect with offloading data size. When the data size increase, it is common the energy consumption and time delay also increase. But here the single agent, this DDPG, dualing, DKWN and DKWN is increase fastly, but the multi-agent scheme is increased slowly. It is better than the single agent. So it's the time consumption and energy consumption is better than the single agent because the agent cooperate each other and share information. Due to this, the energy consumption or the time delay also minimize than the single agent scheme. This one is the task drop rates. When the outage probability in our scenario indicates availability or computation link between agent and computational node capacity and network congestion, we observe that outage probability of offloading task drop rate increase as the size of offloading data increase. Therefore, the multi-agent DRL approach is more applicable for UAV enabled or UAVs enabled IoT network to reduce task drop rate, minimize the computation cost, and improve IoT device. As we saw in the graph, the multi-agent is less outage probability of or task drop rate than the single agent. Here, this is the energy consumption of UAV cluster head. When the number of agents increase that access the UAV, the energy also increase. But using multi-agent scheme, the energy increase slowly than single agent scheme. So, as conclusion, a complete framework, we proposed multi-agent RL-based computation offloading and resource allocation in aerial to ground network in emergency situation. The cluster UAVs enabled IoT network to provide different services such as extend network coverage, act as aerial base station to give provide different service like allocated resource or computational resource or transition power. Computation cost. Our framework was better than a single agent, and outage probability is less than the single agent. Future work, we plan to work on secure computation offloading with energy harvesting in UAV-assisted IoT network, adopting blockchain and machine learning technique. Thank you very much watching this presentation. Thank you very much.
My name is Tomasz Szydło, and I'm working at VH University of Science and Technology in the Department of Computer Science in Kraków, Poland. Together with my colleague Krzysztof Zieliński from the same department and Marcin Jarzom from Samsung R&D Institute, Poland, we would like to present a paper entitled Resource-Aware Log Monitoring Data Transmission for Smart and IoT Devices. I would like to walk you through the agenda of the presentation. At the beginning, I will discuss the motivation of our research work, then the concept of the method proposed in the paper, with some details of the function-driven log processor. Then I will discuss the evaluation and I will sum up the paper with a short summary. Computer systems need to deal with billions of log events and time series data representing their internal state. It's even more important nowadays when we are facing a pandemic situation where a number of people are using smart devices and mobile devices on everyday basis. Commonly used monitoring solutions such as Elastic, Stack, and others are designed to collect and send almost any type of information. But the problem is that resource usage is not a primary concern of these solutions. Using them in edge computing and IoT devices may lead to excessive overheads. So that's why we have come up with the idea of function-driven log processor, which is called FLP, which is a component installed on the monitored system, which receives on its input structuralized log and metric data. This log information, it might be some logs from application in textual form, while time series data, it might be, for example, CPU usage as a time series. So all of this information, raw information, are stored in RRD database, round-robin database, and only subset of them are published to the cloud where they are analyzed by some administrators or, for example, some machine learning-based solutions. So whenever it's necessary to get insight to the data and analyze the raw data, one can send a requirement packet from a cloud to a device and receive all the data from round-robin database as a response. The function-driven log processor introduces two mechanisms to send only a subset of data from monitoring data from the device. One is extended delivery guarantees for monitoring data, and the second one is time series data reduction with on-demand data insight. So to sum up these ideas, function-driven log processor FLP is a component installed on the monitored system. It receives on its input structuralized log and metric information from devices or data shippers like, for example, in Elastic Stack. Two mechanisms are applied to the data before sending them to the cloud. First one, the extended level guarantees for monitoring data, is about sending a data with two semantics, at most once or at least once. So our idea was that not every single piece of log information is very important. So we can send this less important information using at most once semantics. So we are not care about the fact that sometimes this information may be lost during communication. And very important data using at least one semantic. So whenever it is lost, it will be resent from the device to the cloud. And the second mechanism, time series data reduction with on-demand data inside, is based on observation that sometimes we do not need very precise with high resolution information of CPU usage. In most cases, we need only some characteristics with some outliners and the trend of time series. So we would send only this important critical elements of time series, and all the raw data is available for request when it's necessary to process raw data. Function-driven log processor FLP is defined as a function with 4 arguments. F is a function that selects the most important points in the time series data. Later on, we'll show how to select these points in the time series data. And G is a function that selects the most important point in the event series data. It has to be provided usually by system administrator, who knows what information in a log file is important for proper behavior of the system. TS is the length of the batch processing window, because we are processing data in batches. And TR is a retention period for storing original data in the RRD on a device. So the old data from monitoring are removed from the device just to preserve the memory on a device. The extended delivery guarantees can be applied to data based on their importance. TI and EI represent important information that should be sent using at least one semantic. The rest of the data has to be sent with at most one semantics. The protocol based on HTTP TCP, as in ELK stack for example, provide on reliable communication and reduce large overhead. This is mostly due to the fact that TCP is connection-oriented protocol. There are communication protocols targeted IoT devices and devices with constrained resources, for example, COAP protocol, Constrained Application Protocol, which is based on UDP and provides different levels of quality of service, which can be mapped directly to at least once and at most once semantics. We have analyzed also MQT and LWM2M protocol, but decided finally to use Constrained Application Protocol COAP in our solution. We have analyzed several algorithms for selecting most important points from time series. The simplest method would be to lower frequency of sampling, but this may distort the original time series. The second approach would be to reduce the dimensionality of the time series by linear interpolation. But here is the same, we could distort the original time series. But the most promising approach to time series data reduction is to select the subset of perceptually important points, which gives a time series which is very similar to raw time series from human observer perspective. The key idea here is to find the point which exhibits the greatest deviation from the line connecting the first and final point of each series, and then slice the series recursively on that point until we get requested number of final time series data. On the right hand side we can see how the original time series that consists of 600 points was reduced to 60 points, and from human perspective the time series are very similar. Finally, we have decided to evaluate our solution. Our idea was to implement a real service on a real device and to take log data and metric information from this service. and send it to the cloud using a well-known monitoring solution. In this case, we have used Elastic solution. Then we decided to replace HTTP protocol to COAP protocol and analyze what was the benefit of it. And finally, we have decided implemented and introduced time series data reduction just to observe what was the benefit in this situation. Function-driven log parser can be used for any service installed on the device, for example, smart home hub, TV set-top box, smartphone, or something else. In the research, we decided to stimulate the behavior of a device and generate log data by using a very simple HTTP server installed on Raspberry Pi. In the testing scenario, users access a website served on a monitored device. The entire scenario lasts 5 minutes, and up to 60 users access the site continuously. Whenever a client receives the page, it immediately requests it once again. So during 5 minutes, this device faces the request from the users. The testbed that we have used in our experiments is composed of Raspberry Pi on which we have installed HTTP server. It's Apache 2. It's based on it uses Raspbian Linux, and there's installed a file bit from elk-stack just to monitor log data. So we had Apache 2 server logs for analysis. On the other side of the slide, on Cisco UCS, we had two virtual machines, one with elk-stack, which gets the data from file bit and Raspberry Pi, and the second VM which was used as a load generator using JMeter to push HTTP requests to web server and get the results. So this machine 3 with load generator was used to stimulate this web server on Raspberry Pi, and during this testing scenario we collected the log data and analyzed this log data. We've applied, of course, function-driven log processor. Experiment 1 was used to only calculate the throughput of the Apache 2 server, so it was like testing a scenario where users are accessing the web pages on Raspberry Pi, but it was not monitored and observed just only to verify that this scenario is working up and running. The aim of the experiment 1 was to calculate the baseline resource consumption by the protocols used to send log data to the ELK monitoring stack. To increase the indexing speed in the Elasticsearch, the bulk API was used. In Elasticsearch, each log line is converted to JSON files, which increases the size of the packets for about 275%. On the right-hand side, we can see collected the packets using Wireshark, so you can see these JSON files. These are the results of experiment 1. So most important conclusion is and observation is that Elastic Stack HTTP post header is more or less 200 bytes, where TCP header is 20 bytes, so altogether is 220 bytes, while UDP header is more or less 8 bytes. And the second important thing is that compression of log data gives a huge decrease of the data that has to be sent. So when you compare no compression with strength 1, which is of course fast and uses less resources than compression on level with strength 9. So when you compare no compression with compression 1 and compression 9, it's like 100% to 74 to 6%. The aim of experiment 2 was to evaluate the communication protocols with extended delivery guarantees. Basically, we evaluated what we can get changing the communication protocol to provide custom data delivery assurance. We have also analyzed two mechanisms. First one is aggregation, and the second one is a compression. It's very similar. These methods are very similar to the one used by Elasticsearch Stack. It's like bulk data aggregation and compression on with different strength. The communication protocol used by the ELK stack, which is REST TCP based, has been changed to COAP protocol, Constrained Application Protocol. It's a RESTful protocol with get, post, put, delete methods, and transport is defined for UDP. It's very easy to proxy to and from HTTP. What is most important, COAP protocol provides also the transaction messages. This is confirmable and non-confirmable messages. We had to implement two additional modules in Java. This is Elastic to COAP and COAP to Elastic. So in a first figure, we see how file bit log shipper on the Raspberry Pi is sending the log data to ELK stack on virtual machine. So this communication is based on HTTP zipped over TCP. And in a second figure, we see how this communication is intercepted by our modules, and HTTP over TCP is converted to COAP over UDP and sent to the COAP to Elastic module in a virtual machine, and then it's sent to ELK stack. So from the ELK point of view, the communication is the same as it was before, because the traffic is intercepted, converted, and converted once again in a virtual machine on the ELK stack side. In a table we can see results of experiment 2. In the two first cases, messages from bulk API were unpacked, and every single UDP message contained a single line of log file. These values were captured on a ELK stack side, on virtual machine side, on a server side. So we could observe 5% packet lost during experiment in non-comp case, because of the fact that UDP protocol does not have congestion control mechanism and retransmission. But what is interesting in the second case, when we have confirmable messages, we can observe 30% of increase in packet amount due to retransmission and acknowledgements. And in the last two cases with aggregated messages, we can observe that in the non-confirmable messages it was only 660 packets, while in confirmable messages it was 1,522 messages, because we had to send back the acknowledgements and some retransmissions to the log data. The third experiment was to analyze time series data representing the number of requests processed by the HTTP server each second. So we have analyzed a time series from a period of 5 minutes from the whole testing scenario, and we have compared the PIP method applied to the time series representing the number of requests processed by HTTP server each second, and compared these two time series, redacted and the original one. So it's interesting when sending 10% of data point results and accuracy of 96% when calculating the total number of HTTP user requests sent. So we can see that we can aggregate time series data to very small number of points and send this information to the cloud for further processing. And of course, whenever it's necessary to get insight to the data, we can ask the original data from round-robin database installed on a device. To sum up the experiments, we have verified and analyzed two mechanisms introduced to log monitoring solutions for IoT and embedded devices. First mechanism is related to time series data reduction, which uses the perceptually important points method, which extracts the most important points from a human observer perspective. And the second mechanism, which is called extended delivery guarantees, it uses the COAP protocol, Constrained Application Protocol, instead of TCP, and REST approach to the sending the data. And what this gives us possibility to implement at most once and at least once sending semantics, because there's that possibility to send confirmable and non-confirmable messages. As a result, during the experiment, we have achieved the log information size of the transmitted log information reduction by 63% compared to the original Elastic Stack solution. To sum up the paper, the mechanisms introduced by the FLP reduce the amount of transmitted log data by sending more reliably important information and unreliably less important. Usage of efficient binary communication protocol is important because it reduces the overhead introduced by communication header. The applicability of the mechanisms is a trade-off between log information completeness and the cost reduction, better resource utilization, higher scalability, and better efficiency. Of course, this trade-off depends on the system usage and sensitivity to operate on the rough log information. Of course, the system may modify the trade-off depending on the system state, example, normal operation, increased usage, or unforeseen behavior. In that case, the system may send raw data instead of this compressed one, but it has to be figured out with system administrators.
So, good morning, good afternoon, good evening, good night, depending on where you are. This is Lee Selden talking about new ways to estimate blood pressure, heart rate variability, and SpO2 via a smartphone camera, just a proof of concept. Summary. Okay, blood pressure and blood glucose levels probably the two most commonly monitored cardiovascular parameters. Our target in this project was to see how much physiological information we could get from a smartphone camera. So we can use the camera to capture the video of a fingertip. The brightness variation represents a photoplethysmogram, or PPG, which can be captured as frames in a YUV color model. The Y frame values are analyzed via FFT. FFT power features can be extracted, and an MLP can be trained to predict corresponding blood pressure levels. This algorithm yields acceptable values for diastolic BP, DBP, the range, RBP, and systolic BP, or SBP. Also, heart rate variability can be estimated from the FFT power spectrum by comparing the main heart rate frequency with that of neighboring frequencies. A third algorithm uses linear regression to estimate SpO2 on hue variation in the video, which is related to O2 variation in the fingertip. Okay, disadvantage is that the MLP part used for BP is very time and resource consuming. Okay, so I leave you with suggestions for further improvement. So when we put our finger over the smartphone camera, we see a red video. If you're lucky, sometimes you can see the brightness pulsating together with your heart rate. What you cannot see is that the color of the red also changes as the oxygen levels in your finger change. Okay, if we sample this video, this over 15 seconds, and break down into Y, U, and V values, we see how they all oscillate together with the heart rate, especially the Y, the brightness value, can easily be used by peak counting methods to find the heart rate. The U, which is a green-yellow sort of color parameter, and V, which is sort of the difference between U and Y, sort of, also oscillate over time, partly with heart rate, partly with respiration rate, and generally show changes that might be related to differing oxygen levels. Okay, let's start with the SpO2. Okay, as I said, the shade of red in the PPG varies depending on oxygen levels. We can't see it, but we can see the changes in the U and V values. Ideally, oxygenated SpO2 is 100%, while the deoxygenated blood in the veins is about 70%, so a range of about 30%. If you have poor oxygen uptake, for example, at high altitudes, the oxygenated value goes down, thereby reducing the range. So we can hope that hue variations in the video are related to SpO2 values. More hue variation, more variation in U and V corresponds to a greater SpO2 range and a higher SpO2. But hue is also a function of Y, U, and V. Therefore, SpO2 is a function of Y, U, and V. So for our data back in 2013, collected Y, U, and V from video frames from, by holding the right forefinger over a phone camera, and simultaneously had a pulse oximeter on the left forefinger. There were 3 subjects, altitudes from 30 to 4,300 meters. At rest with light exercise, 678 samples were collected. Okay, the results were done by using linear regression with PSPP, using SpO2 as the dependent variable, and various Y, U, V parameters and altitude as the independent ones. So the linear regression gave the equations seen at the bottom. It turns out that with this data, the altitude was a predominant influence on the SpO2, which decreased with increasing altitude. Move on to the BP algorithm. So this took several years of experimentation and trials and errors. So finally, you capture a video, at least 512 frames from the camera, using moderate background illumination, do a FFT on the brightness values, which is the PPG, basically. Extract about 41 features from the FFT power spectrum, which describe the shape of the PPG generally. Train an MLP on at least 100 sets of these features with known training values of SBP, DBP, and RBP. This describes the training data that was basically from myself over a few months. Okay, this shows a couple of screenshots. On the left, this is after recording a video, in this case 539 frames recorded in 32 seconds. On the right-hand side, we have the screenshot after calculating the FFT and the heart rate. So by peak counting, we get HR count is 74.1. By looking at the big peak In the FFT, we get a heart rate of 74. Respiration rate is looking at a peak in the low frequency ranges. In this case, we get 5.9. And the HRV we get by looking at the neighboring peaks in the FFT. In this case, we get a number 0.44. Okay, so this is, at the top, you see a PPG, in this case inverted, so positive is down. And at the bottom is the real part of the FFT. At 0, we have the DC offset. We have a large peak representing the heart rate. Near the heart rate, we have a cluster of smaller peaks, which would describe the heart rate variability. And then higher up, we have what we call the harmonic 1 and harmonic 2 of the heart rate frequency, peaks which describe higher frequency variations in the PPG. Okay, we extract 41 features. This shows a few of them, not so many. They describe the heart rate in hertz and in time. They describe the average power of peaks, heart rate peaks, harmonic peaks, etc. Sums of powers from one peak to the next peak, and so on. Ratios of peak powers, and we also have ratios of powers over ranges of frequencies, sort of the, for example, high range power over low frequency range power, and so on. We also have, we include the SpO2 HRV and wave, PPG wave parameters in the MLP training. The MLP that I developed looks briefly like this. There's a separate MLP or thread for each of diastolic, systolic, and range of BP. The 35 nodes in the input layer represent the 35 features that were used. 105 in the first hidden layer is 3 times the number in the input layer. This is necessary because the PPGs for different blood pressures look fairly similar, and we need a lot of nodes to try to tease out differences. The output layer shows that the nodes, each node represents a bin of 2 millimeters mercury. So 25 for DBP means that DBP values range over about 50 millimeters of mercury. SBP ranges over 120 values, e.g. from about 70 to 190 or so, and so on. Each MLP is run 30 times. Each trial is up to 20,000 iterations, and you save the best of the 30. Okay, this is the dangerous step. This function can freeze your phone by using up all of its resources for hours. Some speed improvements were made. The DBP, SBP, and RBPs are separate threads which run concurrently on multi-core phones. We've changed to single precision floating point calculations because phone FPUs use single precision. And we've done inline coding and a few other little tricks to make it faster. The initial runs were about 20 hours for 154 samples, and we got that down to about 5 to 6 hours. But that's still too much, and we're not sure how to improve it. Okay, this shows the estimate of BP. So we can, to do the calculations, you have to save the heart rate and FFT calculations. run the training thing every now and then. Okay, and then press guess BP, which will tell you what the guesses are for all of the unknown BP recordings, which are indicated with BP values of 111 over 11. Okay, in the message box below, there are all the results with date and time, and above that, the latest result shows an SBP of 112, DBP 78, and RBP 44. Finally, we come to the HRV algorithm. So currently, most definitions of HRV are based on analysis of RR intervals in the ECGs. Okay, we can't get that precision with a phone camera, but visual examination of the FFT yields an easy estimate of HRV. So if the heart rate is a single frequency peak and there's no peak on either side, then the HRV is 0. Okay, but in reality, there's a peak at the main HR frequency, but there are lesser amplitudes, but non-zero ones on both sides, and these amplitudes relative to the main one are a measure of the HRV. So this is a new, very straightforward way to estimate HRV. So preliminary results, we used a very, very simple equation just to see if it delivered some results. In this case, the real value in the FFT at the main HR frequency at HR peak I, and on either side, the values of those frequencies. You sum these side frequencies and divide by twice the main frequency. Excuse me. Okay, so if the side frequencies are 0, it's 0. If the side frequencies add up to the same as twice the main frequency, you get 1. Conclusions. Okay, this work has been only a proof of concept and is not a finished result. Source code is available, as is documentation. On the to-do list for BP, we have optimize the networks, more training data, speed, etc., etc. For HRV, someone could do a very thorough study into the optimal relation among the various peak amplitudes and do correlations of this estimate with activity or stress levels where we know from other work that there are vague correlations. For SpO2, we need more test subjects and more data, and you have to think about the actual value of the altitude parameter because very few people will actually go to Tibet in order to reduce their SpO2 levels. So I'd like to thank Sternly Simon, especially, and Geoffrey Sutanto for help with this project. Thank you very much. Bye.
Hello everyone, my name is Ong Yi Ling and I am from Swinburne University of Technology, Sarawak campus, Malaysia. Today, I would like to share about my research project, which is detection of vertically oriented text in images containing natural scenes. Dr. Lau Bi Teng, Dr. Almond Chai, and Dr. Chris McCarthy are my supervisors. Dr. Lau Bi Teng and Dr. Almond Chai are from Swinburne University of Technology, Sarawak campus, Malaysia, whereas Dr. Chris McCarthy is from Swinburne University of Technology in Melbourne, Australia. First of all, text is an important avenue that provides information and for people to communicate. For example, there are signage or road signs that contain text. These tags are important as they provide important information about the happenings around. For example, text detection helps people with visual impairment to travel around independently, such as getting the directions or identifying objects. In general, there are several common types of text that appears in natural scenes. For example, there are horizontal text, arbitrarily oriented text, curved text, and also vertically oriented text. Since detecting text is important, various researchers have proposed different approaches for text detection system. The scope of text detection has grown wider today, as it is able to detect text of different orientations, which includes horizontal text, curved text, and also arbitrarily oriented text. However, there are very few research done on vertically oriented scene text detection. In general, images that contain text can be differentiated into two categories, which are scanned document and scene images with text. Using the traditional method, optical character recognition, which is also known as OCR, it can easily detect text in scanned documents. This is because they normally contain clean and uniform background. However, for text detection in natural scene images, it is more challenging due to the complicated backgrounds with other objects in the scene images. For example, some objects tend to have the shape of text. Various text orientation, different font types, and font sizes. The quality of scene images can affect scene text detection as well, when some of the images shows low resolution and blur images. For vertically oriented scene text, they can be differentiated into three different types, which are bottom to top vertical text, top to bottom vertical text, and also horizontally stacked vertical text. For bottom to top vertical text, we read the text from the bottom to the top. As for top to bottom vertical text, we read it from the top to the bottom. For horizontally stacked vertical text, the letters are arranged in a horizontal way, but they are stacked up vertically. As I've mentioned, very few research has been done on vertically oriented scene text detection. Capture to text, which is proposed in the year of 2018, it is a model that is able to detect horizontally stacked vertical text, but not for top to bottom and bottom to top vertical text. At the same time, capture to text only works on images where the user have to select on the text region manually. There is another model which was presented by Choi Yoon et al. Their model is able to detect horizontal text and horizontal stacked vertical text only, as shown here. However, the model proposed is unable to detect top to bottom and bottom to top vertical text. So here are the research problems. As scene text detection has become a popular research topic, most of the recent research on natural scene text has invested in modeling horizontal text, arbitrarily oriented text, and also curved text detection. However, detecting vertically oriented scene text is equally important as they may carry important information. And we cannot deny that there are many vertically oriented texts that appears at our surroundings. As to that, there are some research that is able to detect vertically oriented scene text, but not for all bottom to top vertical text, top to bottom vertical text, or horizontally stacked vertical text. Now, I would like to share about the conceptual model that I've proposed for text detection on vertically oriented scene text. In this proposed model, multi-directional text detector, which is also known as MTD, is introduced. MTD detects vertically oriented text on top of horizontally oriented and arbitrarily oriented text in natural scene images simultaneously. First of all, the input image will undergo the process of MTD. In the beginning of the framework, the convolutional layers of VGG16 model is implemented. After that, the convolutional feature map, which is generated by the last layer of convolution layer, is obtained using convolutional neural network, which is CNN processing. Next, MTD implements the idea of Region Proposal Network, which is RPN. Region Proposal Network is the true backbone of this algorithm, other than convolutional neural network. So what is Region Proposal Network? This is a small network which slides over the convolutional feature map using rotation anchors, which is also known as R anchors. For different orientation of text detection, the idea of R anchors is used. R anchors of different scales, different ratio, and different angles are introduced. As shown here, R anchors with the scale of 8, 16, and 32 are used. As for different aspect ratio, they are 2, 5, and 8. Besides that, there are 6 different angles of rotation anchors proposed as shown in this figure. From the rotation anchors generated, we have to determine whether the detected text region is a positive or negative anchor box. This can be determined by calculating the value of intersection over union, which is IOU. As shown in the equation here, IOU shows the overlapping between skew ground truth area and the rotation anchors. So, if the value of IOU is more than 0.7 and the intersection angle is less than pi/12 radian, then it will be considered as a positive rotation anchor. The purpose of calculating the value of IOU is also to eliminate the negative detected text regions. After that, followed by rotation region of interest, which is known as RROI. RROI pooling here is different from the traditional ROI pooling, as it is able to pool at any region. As you can see here, the rotated proposal region can be divided into subregions. And lastly, max pooling is performed in each of the subregion. And finally, it shows the text regions in the bounding box in the image. For evaluation purposes, these are a few public datasets that we have used to compare the performance of the proposed model in detecting text. For example, there are ICDAR 2013 dataset, ICDAR 2015 dataset, and also MSRA TD500 dataset. These are the public benchmarking datasets that are used to evaluate the performance of text detection. For ICDAR 2013 datasets, it consists of mostly horizontally aligned scene texts as shown in the images here. For ICDAR 2015 dataset, it consists of both horizontal and oriented scene text, whereas for MSRA TD500 dataset, it consists of multi-oriented scene text. So far, there is no public benchmarking dataset that concentrates on vertically oriented scene text. Therefore, I have collected about 700 images of vertically oriented scene text as one of my datasets. These are some of the examples of images that I have collected. It consists of all 3 different types of vertically oriented text, which are horizontally stacked vertical text, bottom to top vertical text, and also top to bottom vertical text. Here are some of my results and discussion. This is a preliminary testing carried out to evaluate the performance of text detection using rotation anchor boxes with different ratio, different scale, and different angle as mentioned previously. Therefore, these rotation anchor boxes not only detect horizontal text and arbitrarily oriented text, but also detect vertically oriented text in natural scene images. These are some examples of the successful vertically oriented scene text detection, where the red boxes here shows the location of the vertically oriented scene text in natural scene images. For evaluation purposes, there are three quantitative measures used to measure the result of detection. They are precision, recall, and F-measure. For precision, they can be calculated based on this equation. They are used to evaluate the confidence of the algorithm proposed by calculating the percentage of the text regions detected correctly compared to the text region claimed. The true positive here indicates text regions that are predicted correctly, whereas false positive indicate the text regions that are predicted wrongly. Besides that, recall is also calculated to determine the sensitivity of the algorithm. Based on the equation of recall, it provides a ratio of the number of correct estimates to the total number of targets. As for F-measure, it is a harmonic average that combines the figure of both precision and recall into a single measure quality. The equation of F-measure is as shown here. Here are the results obtained from the preliminary experiment. The performance of NTD was evaluated using these three quantitative measures, which are precision, recall, and F-measure. The result shows that NTD achieves a precision of 87%, recall 76%, and F-measure at 81%. Besides that, these are the results obtained using the three public benchmarking datasets. The result shows that the proposed model shows an average performance as compared to the other existing methods, where it achieves 87% of accuracy for ICDAR 2013 dataset, 73% accuracy for ICDAR 2015 dataset, and 72% for MSDA TD 500 dataset. However, the proposed method is able to detect vertically oriented scene text at the same time with the performance of 87% accuracy. So, in conclusion, detection of vertically oriented text could provide additional and useful source of information to understand the natural scenes. Thus, this research proposed is to develop a model for detecting vertically oriented text in natural scene images autonomously, where the performance of the proposed model shows an accuracy of 87% on detecting vertically oriented scene text on top of detecting horizontally oriented and arbitrarily oriented scene text simultaneously. And that is all for my presentation. Thank you very much.
Hi everyone, my name is Hamra Jawahiri. Today I'm going to represent you our paper regarding how far could wearable augmented reality influence customer shopping behavior. I would like to first shortly talk about AR and our study motivation, then I will give you some insight about the materials and the methods that we use in the study. Later, I will present you the results that we gathered, and at the end, I would like to also talk about the limitations that we faced. Before I start with study motivation, I wanted to talk about augmented reality, or shortly AR. So what is this AR? Augmented reality, or AR, combines real and virtual objects in a real environment. So although the augmented reality was initially conceptualized by Morton Heilig in 1962, the term of augmented reality actually was introduced by David Mintzel and Tom Caudle in 1992. Augmented reality is a part of mixed reality in reality-virtuality continuum, which was defined by Milgram and Chinyu in 1994. We all somehow heard about AR from somewhere at some point in our life. Of course, there is no one haven't heard of Pokemon Go, right? Which is one of the most popular examples of using AR. But as I said before, AR is actually a lot older than that, so it's been in our life for a very long time. So did you know that all of these marks and numbers merged to an actual video stream of a soccer match is also an example of AR? Yes, they are. So I can hear you saying AR is not also a new matter to the shopping either. So let's talk about shopping. Everyone loves shopping, right? Who doesn't? And especially if you're a fan of online shopping like me, nothing could replace the comfort of buying stuff when you're sitting in your couch in your own living room. At least this is what advertisement says, right? You know, nowadays we're trying to fit all of our everyday routine into the digital world. Well, online shopping is not a new concept actually, and it's been around for a while now, but there is always this trust issues when it comes to buy something online. Well, at least there was some trust issues until pandemic, when buying online was an option, not a necessity to adapt our routines to a completely digitalized life. But because only we have to do something, that doesn't mean it is our preference, right? So let me explain this with a very simple example. We as a human are living in a 3D world. Above anything we believe on, everything that we could see, we could actually feel it. So, for example, look at this room. So imagine you're in it. So there is like a notion of the 3D environment to this video. So you can rotate, you can see, you can feel stuff. So you can get the feeling of every object that's been in this environment. For example, look at this cute cushion. So it's on the couch, you can feel it. There is a reality notion to this cushion. Or let's say this is a very cute tree-leg lamp over here, and also there is a cute little chair, a very nice green color, or like there is also a very cute rug on the ground, and you know, we can feel it. Every object in this room has a reality to it. So what happens when you try to sell these really 3D objects with only 2D images? Yes, actually it is where exactly the trust issues arises. So look, for example, here there is images of the rug from the previous slide, from the previous room. So how much could the customer trust this advertisement? So let's make it a bit more realistic. Let's add another realistic image of it, or maybe even better, one which look like the images from the home decoration magazine. Or let's make it even better and also add more some detailed information to it. But as you can see, this advertisement method is not similar to the experience of shopping in actual store because of the lack of 3D notion or lack of this feeling about the product. So what we have done is, of course, we are humans, we are better than that. So what we did, or let's say we tried to do, was putting, this 360 degrees rotatable objects of the stuff alongside of 2D images as a visualization option. But as you can see, but still there is something not quite right about it. Even though when we represent the 3D model of a product to a customer, it doesn't seem to solve these trust issues. I can tell you why. Because the product images are not the only 2D guys in this scenario. All of our 3D models are being locked up behind 2D displays, which means it doesn't matter how much we try to make a perfect 3D model of a product, we will never solve our problem until we are not restricted by 2D displays. So coming back to our study motivation, we wanted to see actually if we get rid of these 2D displays and use a wearable augmented reality device instead of non-wearable AR tools to not only have 3D models but also have a notion of merging these 3D models to our physical world would actually help to improve the shopping experiment. So we set the following aims for our study. We wanted first to evaluate customer attitudes toward the AR as a method and also towards the shopping while using AR. And also we wanted to see the potential of the commercially available devices for this purpose. As a material, we use Microsoft HoloLens as a wearable augmented reality device and a Windows-based tablet. In order to fulfill the requirements of this study, we designed an app to simulate the shopping environment. Since complexity plays as a barrier for new technologies and experiences, the app was simplified as much as possible. In the app, we added 33 objects from different categories with prices less than 50 euros. The prices was actually the average price for the product. It was not a lot cheaper or more expensive than what they actually are. You could go to the next or previous objects using the buttons. Like any shopping app, you could open the shopping basket, make some changes in there, and of course purchase items by pressing the buying button. And meanwhile, all of these interactions with the app is being recorded in the background. So we installed the same app on both HoloLens and the tablet to reduce the variables in this study. So AR would be the only feature or variable in shopping simulation. Here is a view of the steps of purchasing an item in HoloLens application. Sorry for the quality of the images here, they are a bit low because they were captured from the HoloLens camera, but in reality the quality was actually quite high, so sorry about that. In the app you could visualize the 3D models of the item in the menu, and you could also rotate them if you like. If you're interested, you could also add the item with actual dimensions into your room. You could move them or rotate them in a way that you wanted. If you like the object, you could add it to the basket and you could check your order summary and edit it if it's necessary. And at the end, you could place the order by placing the buy button. As I said before, the application in the tablet is exactly the same as HoloLens app, with an exception that in the HoloLens you could visualize the product in real environment using augmented reality, where in the tablet you could only see the objects in the menu. As you can see in here, we had 20 eligible participants for our study. All participants were asked to fill out a general questionnaire about basic information, their current knowledge and their attitude toward technologies before starting the experiment. Later, the participants were randomly divided into two groups. While first group experienced HoloLens app first, the other group started the tablet application, and later the groups switched the devices and experienced the app overall again. Participants were explained how to use the application on each devices, and they were taught the hand gesture, and they were allowed also to interact with the devices for a few minutes to feel comfortable, and after that they started the application. After each experience, they were asked to fill out a detailed questionnaire regarding the overall experience that they had. And at the end, we also asked them to fill out the final questionnaire to compare their experiences. We had 20 volunteers, 10 males and 10 females, with a median age around 28 years, which made the population limited to Generation Epsilon. And all of our participants had a higher education level or were students at the time of the survey. The experiment took place in a room with basic furniture, including desk, chair, phone, and whiteboard, allowing participants to try and place the offered objects freely. To collect the primary data, multiple standardized English questionnaires were designed, and questions were mainly based on itemized rating scales. In addition, we also added a few multiple choice questions. We also used the interaction data that we gathered from the apps to evaluate the behaviors of the customers. As I said at the beginning, we wanted to separate our evaluation in terms of impacts of methods and impacts of used devices. First, where we evaluate the aspects of AR as a method for shopping, and second, investigating the usability of used devices for this purpose. So we made separate questionnaires that touches different aspects of the experience. Here, as you can see, yellow color indicates augmented reality method, where purple shows the conventional 2D shopping method. As you can observe in this graph, according to the participants' idea, AR is more dominant in being joyful, realistic, and influential. And naturally, due to the fact that the experience was new for some participants, conventional method was found to be easier to integrate in. Here we can see the results of comparison between two different devices. Half of the participants rated their overall shopping experience with HoloLens as good, and the other half rated the experience as excellent. However, only half of the participants rated their overall shopping experience with tablet as good, and no one actually rated the experience as excellent. 9 participants rated their experience with the tablet as indifferent, and sadly, 1 person rated the experience with the tablet to be bad. We couldn't actually find any significant difference between these two groups of tablet first and HoloLens first regarding the overall experience, and the p-value for the HoloLens experience was 0.48, where the p-value for the overall experience with the tablet was 0.63. We also investigated the participants' thoughts on impact of AR in their attitudes towards shopping. As you can see here, they mostly agreed that AR had an impact on understanding the product in a good way and assisted them in making a buying decision. However, it doesn't seem like AR could actually create a shopping experience similar to the real-world store. According to the data that we gathered from the applications, we could also observe that even though there was not much difference in the number of added objects to the basket, but there was a significant difference when it comes to purchasing the item. Similar here, we could also see that the amount of money spent in AR application is not much different than what was added in the basket initially. However, it's not the same for the tablet case, which shows that AR actually helped to increase the confidence of the buyer towards shopping. Here is another aspect that we asked participants. We asked them which product category they think would be the most suitable one for each method, and we got these results that you can see in these graphs. Interestingly, we also asked them which method would they prefer to use in future for their online shopping, and they mostly preferred AR. Of course, our study had some limitations, namely the variety of the products, sample size, and experiment environment. Of course, shopping is highly relied on individuals' needs and preferences, and obviously we couldn't add all of the available products in the app, therefore we needed to limit the number of the products for this study. The other limitation was our sample size. In our upcoming work, we are also planning to increase the sample size and the variety of the products to get more general results. It's also worth to mention another limitation of our work, which was the experiment environment. In our study, we used a fixed room for experiment, which might also have an impact on attitudes of participants towards shopping. Maybe in our future work, we will conduct an experiment with a flexible environment where participant could actually choose where he or she wants to perform the experiment. To conclude, I want to mention that even though AR is not yet as common as other shopping methods, we saw that it helped to improve the overall shopping quality and the experience. Maybe in future we will see AR more in the shopping field, and we will see the improvement alongside with the AR. This was it for my presentation. Thank you so much for your listening.
Hi everyone, this is Amna Batul. Today I'm going to present about the paper I have submitted in MobiQuitous EAI 2020, which is about towards a system for aged care centers based on multi-user, multi-device interactions in IoT collectives. Let's begin. What is IoT? Of course, most of us have an idea about Internet of Things, which refers to a system of interrelated internet-connected objects that are able to collect and transfer the data over a wireless network. Now, in most cases, we cannot consider the IoT as a single smart device, but as IoT collectives, which means the number of internet-connected smart objects and the functions they perform within a particular IoT system. This is what we refer to as IoT collectives. In this research, first of all, I would like to tell you about these three different images. In the first image, as you can see, a user is trying to interact with a smart robot. In the second picture, a smart drone is controlled by a user using the hand gestures. And in the last picture, a Siri on the mobile device or a voice assistant system is usable by the user using his voice. Now, these devices, such as the robot, the drone, and the smart mobile, these three devices or many more are considered as smart IoT devices. And when a user is interacting with these devices, we refer them as human IoT interaction. What if we have multi-human or multi-user, multi-device interactions in IoT collectives? What is multi-user, multi-device? In this research, we are going to look into how different users or multiple users interact with multiple IoT devices within IoT collectives, and how these devices in return handle the interactions from these multiple users. And we have referred this as multi-user, multi-device interaction. In this research, we are going to develop a system, but we have already developed a system for aged care centers based on multi-user, multi-device interaction in IoT collectives, which is the aim of this research. What is the concept that we need to talk about when we are going to implement a system or when we are going to develop a system for aged care centers? The main concept that we are going to talk about is, first of all, we need to consider that we have multiple homes, okay, and we have the aged care centers. In aged care centers, the seniors has been admitted, and these seniors are being admitted by their family members. Now, if these family members want to interact with the seniors in aged care centers, they can use the smart mobile devices sitting in home instead of visiting these aged care centers every day. What they need to do is, the users in home or the family members in home needs to use their mobile devices to send a request to the multiple robots placed in an aged care center with the smart sensors and the actuators to please interact with the seniors and get back to us. Interact with the seniors means to monitor these seniors, to see if they are good in health, if they are being taken care by the carer staff members, they are providing the quality life to them, they are taking care of them properly. Once the robots will finish tracking them or monitoring the seniors, they need to pass the whole data they are receiving by the seniors to the Firebase, or you can say the database server. Now, the database server, the whole data that is being placed can be retrieved by the family members using the same mobile devices they have used to interact with these robots. In this case, in aged care centers, we cannot forget about the carer staff members, because these smart robots can also assist these carer staff members. So what carer staff members have to do is they also need to use their mobile devices to interact with these smart robots, so that they can ask the smart robots to please visit their offices and store the specifically medical measurements, including the seniors' sugar level or the blood pressure, and store that data on the Firebase so that the family can also retrieve the medical measurements, not only the simple seniors' photo or asking the daily routine questions if they are feeling good. So with those daily routine questions and the smart and the photo, the smart robots can also store their medical measurements. Now we have multiple interactions in this scenario. First, we have robot family interaction, in which the robots are interacting or acting as a mediator between the family members. Next, we also have the robot senior interaction, where of course the smart robots are interacting with the seniors while taking their photo and asking the daily routine questions to see if they are feeling well every day. The last interaction in our system is the robot carer interaction, where of course the carer members are also interacting with these smart robots. So we have three different interactions in this system. So as during this concept, I would also like to say that by completing this research, we have seen some issues that are decision-making transparency, handling uncertainty, and appropriate behaviors. When we are placing the smart robots or any smart device in aged care centers or in a public environment, we need to be very careful about these three points, because it is important for these smart robots to make the decisions appropriately. As you can see, these smart robots are taking multiple requests from the carer members, from the family members. So it should be easy for smart robots to take a decision appropriately, that what request they need to tackle first. Likewise, they need to check, for example, they are receiving multiple requests from the family members to monitor their multiple seniors. So smart robots has to take a smart decision that on which senior they need to first monitor, and then they need to move to the next senior. Now, during interaction or during monitoring the seniors, it is also very compulsory for the smart robots to handle the uncertainty, which means to handle the failures. What if the door is closed where the senior is sitting, or where the robot has to approach them to monitor them, right? So in that case, the robot has to tackle that task appropriately. Last is the appropriate behaviors. In appropriate behaviors, when the smart devices are interacting with the seniors, they need to be very careful about the consensus seeking process. Of course, the smart robots need to ask the senior before taking any action. Let's say if robot is going to take the senior's photo and senior is not comfortable in that, so robot has to first seek an approval. If they allow the robot to take the photo, then only the robot should proceed with that. Else the robot should take a decision smartly on those requests. If, let's say, if senior has denied to the robot to take his or her photo, then the robot has to be very careful in that case. Either it needs to report back to the family that, your senior do not want me to interact with him now, or it needs to transfer that request to the next robot, maybe to monitor the same senior after some time when the senior will feel comfortable. So in that case, these smart devices have to behave appropriately while interacting with the seniors or the carer staff members. So these are three different issues that need to be considered. And these three issues been emerged by completing this research. So this whole concept is having multiple users who are interacting with multiple devices by creating the multiple interactions in IoT collectives. This whole system is being implemented, it is being prototyped, and we have named this system as Kate. So in Kate, we have multiple different Android mobile applications. Specifically for the family members, we have the family apps. For the carer for the carer members, we have the carer mobile apps. And for the Tami robots, here you can see that this is the Tami robots that we have targeted in our research. So the Tami app is being installed in the smart Tami robots. Now, as I have said earlier, that in this Kate prototype system, we have multiple interactions. So these multiple interactions are designed and presented using state transition diagrams. State transition diagrams to present that when how the robots are taking actions and what states they are representing based on receiving the different requests either from the family or from the carer. In this robot family interaction, the green color represents the family states and actions, and the blue color represents the robot states and actions. If I give you an overview on this without going deeply into this interaction, then I would like to say that the family is, of course, starting a request by sending that request to the particular robot to monitor their senior who is in the aged care center. So family member has to open its app, of course, and then it needs to see that it needs to select the senior's name to send it out to the robot so that the robot knows what senior it needs to track and monitor. So the family has to see that if robot is available, and then the robot will start responding by activating itself and then examining the requests. Why examining the requests? Because we have multiple requests, or either from the carer staff members or the family members. In case if it is a family request, then yes, the robot, of course, will start moving towards the senior's location. It will see where the senior is. And if the robot will find the senior, then it will start interacting with the senior by asking some questions that if you have taken your meal today, have you done with your exercise, etc., and so on. After asking the questions, yes, the robot has to take all the answers from the senior, and then it needs to process those answers. And finally, after receiving all those answers, it needs to store the data on the Firebase server that will be retrievable by the family. So here we have one more feature that seniors can ask the robot to follow them. So in that case, while the robot will interact with the senior, it needs to wait for senior's command. Let's say if senior wants the robot to follow them, then the robot will start following the senior. And once the senior will abort the follow me, the command, then the robot will stop following them and start with the next request, and it will go back to examine the next request. In the same way, we have also designed the robot carer interaction because it is really very important to show how different actions are carried out based on the request the robot is receiving from the carer or the family. All right, let's conclude the presentation. So we have prototyped the Kate system to show that how different smart IoT devices can interact with different users. And also we have considered some of the issues, including the decision-making transparency, handling task failures, and the privacy respecting. So we have created the smooth interaction between the smart devices and the smart devices and the users in IoT collectives, because it is really very important. But at the same time, we need to see that how these the users can interact with the multiple other smart devices, or how these IoT devices can interact with other smart IoT devices. And also these devices can be usable by multiple parties. In our case, we have seniors, the family members, and the carers, but we need to see that how we can maximize the utility of such devices in these interactions. We have used the Tami robots, of course, because it is really very useful. It has reduced the installation of multiple cameras in each room to see if the seniors are taken care well by the carer staff members. So we have used the Tami robots instead of the multiple cameras. As it is an ongoing research, so we are still working on handling the uncertainty, and we are seeing how we can implement the decision-making transparency process and realize the privacy respecting behaviors in Kate system. This was all about the Kate. This was all about our research. And I just want to say that we are not only considering the smart robots, but multiple other smart devices. So it was just a scenario where we have used the smart robots to explain that how multiple interactions can be created between the multiple users and the multiple devices in IoT collectives. Thank you so much.
Hello, my name is Liu Yanwen from Bidirectional University. Now I will introduce our recent research on proactive connection migration QUIC. If anyone has more questions, you can contact us by the following email. Now I will give our report. Loading as soon as possible is the goal that Internet service providers always pursue. In addition to server concurrent processing delay and front-end rendering delay, network link delay is the most important cause of slow web page loading. Some ISP's backbone networks have hundreds of GB traffic per day as attack traffic. This attack traffic also affects the stability of network links. At present, there are many solutions to improve the loading speed of web pages in the industry, such as CDN optimization, DNS profetch, and long connection. However, HiNets can only optimize network performance in the access network and cannot achieve end-to-end path selection and performance optimization compared with the performance optimization stream of HiNets. QUIC is at a higher level in the network architecture and has a more comprehensive understanding of the end-to-end network status. Therefore, in the process of network evolution, the connection migration mechanism of QUIC will make up for the deficiencies of HiNets in end-to-end path selection. QUIC UDP Internet Connections is a UDP-based transport protocol designed by Google, which aims to provide multiplated streams over an encrypted transport. The QUIC has so many features which can significantly improve Internet transmission efficiency and user experience, which is a providing transport protocol. Due to QUIC has some features such as low latency connections, improved congestion control, multiplexing without heterogeneous blocking, forward error correction, and connection migration. It brings some benefits such as when underlying network changes, as long as connection ID unchanged. It can be considered as the same connection. Therefore, QUIC can replace user to explore and select the optimal network. So, in the article, we propose a PCM mechanism for QUIC, which fills the gap in QUIC to optimize performance in highness through path exploration. We propose a path exploration model based on MAB model. For different application requirements, PCM can select the optimal path from different dimensions. We propose a PSA based on UCB, which aims to minimize the cumulative response delay and jitter. Finally, we implement an open-source PCM prototype based on QUIC. At the same time, the trigger conditions adopted by PCM are different from connection migration. The former is active exploration and the latter is passive handover. The combination of PCM and traditional connection migration is the most efficient. The connection migration of QUIC allows a client to change its IP address in the middle connection without having to re-establish the connection. PCM is an active exploration which improves QoE and brings economic efficient. We consider the PCM includes two different stadiums: the steady response time and the non-stationary response time. PCM requires OS, physical support of the mobile terminal, and QUIC support. In the left picture, there are three ways for the UE to access the Internet, through the Wi-Fi, LTE, 5G to the Internet. In the right picture, the environment in different scenarios such as indoor, outdoor, subway, and high-speed environment so on. Therefore, in our solution, there is no need to make any changes on the server side. The current QUIC server can support the PCM mechanism. We only need to change the packet sending, logical QUIC lint, and complete the environment of the quality of different network passes to support the PCM mechanism on the client side. In addition, the PCM mechanism allows the use of the key exchanged in the previous connection establishment without having to redo the HTTP handshake. QUIC connection includes three stages: connection establishment, data transfer, and connection termination. QUIC client first obtains all available IP addresses of the machine through NAT. Then, QUIC client randomly selects a IP and initiates a connection. During the connection handshake, the handshake must negotiate a variety of transmission parameters, including connection ID. QUIC client selects the network path used by each client request through polling, random, or the strategy scheme. PCM records the round-trip delay of the data packet and its response time in turn. And the processing logic is consistent with native QUIC. Stream state management maintains stream status information, including stream establishment time, end time, and total transmitted bits. Total bytes represents the total number of bytes transmitted on one stream, and its function is to normalize and compare streams of different lengths. For streams with a considerable number of bits, we can use the response time to evaluate their efficiency. For streams with different numbers of bits, we can use the response time per bit to evaluate their efficiency. The stream and connection closure of PCM is similar to QUIC, including three situations: normal termination, abrupt termination, and connection termination. PCM needs to find the best communication path for users as soon as possible through less exploration. This model is a path selection with discrete states, which is a typical multi-armed bandit problem. The traditional MAB pursues the maximization of accumulated profit, which is a model that doesn't care about the process, only the result. However, In internet services, users are not only seeking extreme low response time, but also long-term fluency. In general, the path selection strategy, or PCM, can be described as the following process. In the beginning, PCM's routing strategy was a random selection under unknown environmental information, each step of which was explored to find a new path, and network quality distribution information was accumulated according to the response time. After a period of time, PCM repeatedly selects among key passes. Any path will return a result that conforms to a stable probability distribution. Because we use response time as a reward, and we consider that different services have different delays and jitters. Therefore, the goal of PCM is to minimize the weighted sum of total response delays and fluctuations over a period of time. The response on path K consists of two paths, the exploration and the exploitation. The first part is the average value of the historical response delay, which represents the delay performance of the path. The second part is the variance of the historical response delay, which represents the jitter performances of the path. In the formula, the values of A and B depend on the upper layer application of the PCM. In OPS, PCM always chooses the path with the most likely smallest R key. The lower bound confidence for this path is the smallest. In BPS, PCM chooses the path with the smallest upper confidence bound. The right part in the square, which means if the path is selected a few times and the confidence interval is very wide, it will tend to be selected. If the path is selected a lot of times and the confidence interval is very narrow, then the path with a small reward tends to be selected multiplied times. The algorithm logic is on the right part. Since our evaluation of cumulative regret includes delay and jitter, we need to perform a weighted summation of the accumulated regret of delay and the accumulated regret of jitter to evaluate the effectiveness of the algorithm. The regret rule after T runs can be expressed as the algorithm updates OI every time it receives a response time. QUIC uses a non-blocking multiplexing mechanism. The response time is updated with the completion of the stream, which is extremely efficient. Because the existing mobile device OS does not provide developers with the authority for advanced programming of multiply network cards, we have to use a Linux server with multiply-nix as the QUIC lint. The QUIC server is a cold host deployed on the Tencent cloud, and it runs the QUIC server, a program to respond to requests from the QUIC lint. The response delay can well describe the user experience, thus avoiding the problem of too many evaluation indicators. We use the response time to represent the user experience. That is, the smaller the response time, the better the user experience. The picture demonstrates the response time per round of the four states. X represents round, and the Y represents response time. From the picture, we can see that, in general, the response time of the upgrade strategy shows a downward trend. The two PSA strategies further reduce the fluctuation of network delay by selecting the optimal path for transmission, especially the PPSA strategy. Its response time has been significantly lower than the other three strategies. The reason for this result is that the performance of Path 2 and Path 1 are close, and the probability of optimistic PSA strategy switching between the two paths is greater than that of pessimistic PSA strategy. From calculate, we can draw the conclusion that compared with polling, the mean and variance of the 1000 round, so the best algorithm is the optimistic PS. Accumulated regret is an important indicator for evaluating PCM. As shown in the app picture, the accumulative regret of the polling strategy is orders of magnitude different from the other three strategies. The two PSA strategies are significantly better than the other two strategies, which shows that the PSA strategy is closer to the optimal exploration strategy. In most runs, the latter three strategies chose path 2 as the transmission path, which shows that path 2 is the optimal path under the current experimental condition. Accumulated regret is an important indicator for evaluating PCM. As shown in the app picture, the accumulative regret of the polling strategy is orders of magnitude different from the other three strategies. The two PSA strategies are significantly better than the other two strategies, which shows that the PSA strategy is closer to the optimal exploration strategy. In most runs, the latter three strategies chose path 2 as the transmission path, which shows that path 2 is the optimal path under the current experimental condition. Comparing the influence of different combinations of A and B on path selection, there are A equals 0.8, A equals 0.5, and A equals 0.2. In the 15 rounds of path selection, the first two finally selected path 2 as the best transmission path, and the third selected path 1. This result shows that PCM can meet the path requirements of different values of A and B. When applying the PCM mechanism in QUIC, we can choose the emphasis on the path response time, expectation, and variance by setting A and B. The picture on the end shows the path delay changes. We changed the network delays of path 2 and path 3 in the 100 and 600 runs. Through this experiment, we can observe the ability of PCM to adapt to drastic changes in the network and different acts. PCM uses the user's multiply request actions to try different access methods of the current user and explore the quality of different paths. Then PCM finds the optimal access path for the current service through online learning. At present, PCM being QUIC to complete the path exploration and utilization is a very feasible solution for the mobile internet. As mentioned earlier, the deployment of the PCM mechanism in QUIC is not only a technical issue, but also an economic issue involving equipment vendors, ISPs, and users. PCM combines advanced congestion control and application adaptive technology to enable users to obtain the best volume and video call experiences. Thanks for listening.
Hello, my name is Stanisław Saganowski and I'm Assistant Professor at Wrocław University of Science and Technology, located in Poland. Thanks to the organizers for this opportunity. Today I wanted to introduce to you our approach for conducting field studies in affect recognition problem. We call it WELAF. A crucial part of such study is selection of a device for collecting physiological data from participants. Therefore, we'll spend some time talking about devices available on the market that suits a given problem. Supporting well-being is not a trivial task and requires constant monitoring of the participants. Let's take kids for an example. Obviously, we want the best for our kids, not only in terms of their health and financial situation, but also, or especially, in terms of comfort, positive feelings, sense of love. We care a lot about our kids. We would like to know how was their day at kindergarten or at school. Was it fun or they were upset? Maybe they had an argue. Maybe someone broke their heart. If we knew that, we could support them or undertake some actions to protect them. But how can we know that? Kids, in general, never tell the truth. Even if they do, they commonly don't tell you everything. Same thing about elderly people. Either they do not want to share how they feel, or they are unable to let us know due to their illness, or they are simply not aware that their state has worsened. So how can we know that? How can we know what they feel without even asking? In our opinion, the best solution are ubiquitous wearables operating on physiological and behavioral signals, as they offer a constant and real-time monitoring. But the question is, which device should we choose? What factors should be considered? Is the best device the best for every study? Let's answer this question one at a time. We consider 5 research tasks: emotion recognition, stress detection, monitoring and guiding meditation, sleep analysis, monitoring and tracking activity. For each task, we perform a literature review to find physiological signals that are the most significant for completing this particular task. The number of green dots means how important are data from particular physiological signal in a given research task. As you can see, the brain activity, EEG, is the biggest contributor to all tasks except activity tracking. This follows the intuition that the brain is behind every action we undertake. And once we read the brain, we know what the people are up to. Unfortunately, EEG measurement is very inaccurate when people are in motion. Therefore, EEG is not useful in activity tracking and also not applicable to most of everyday life situations. Researchers who would like to analyze emotions or stress in the field have to rely on the electrocardiogram, ECG, blood volume pulse, BVP, and electrodermal activity, EDA, signals. Collecting the skin temperature, respiration rate, and environmental information might be also beneficial. Meditation is a stationary activity, so EEG may be applied. Besides EEG, electrocardiogram, blood volume pulse, or respiration rate might be also helpful. The best method for gathering data in sleep studies is called polysomnography. It requires advanced medical equipment to monitor brain, eyeballs, and heart. For less accurate studies outside the medical facility, accelerometer data, blood volume pulse, and blood saturation might be sufficient. Finally, when it comes to the physical activity, research commonly focuses on the identification, tracking, and quantification. The most frequently used sensors providing data to tackle these problems are accelerometer, gyroscope, and GPS, as well as PPG providing blood volume pulse and ECG. Okay, so we know which signals are important for these domains. So we have to make sure that the device we consider is able to record these signals. Let's move to other factors. The list is ordered as we consider factors at the top of the list to be more important than the factors at the bottom of the list. The ability to provide relevant and rich data in a raw format is absolutely crucial. Many producers develop dedicated applications for end users to allow them convenient monitoring of the data collected by various sensors. However, this data is usually processed in some way, for example, aggregated, filtered, or smoothed, and very rarely available to download. Thus, not useful for the research purpose at all. Some manufacturers provide the ability to access raw data by integrating with a device over Bluetooth or another protocol. Such integration is sufficient to gather data for the research, but still has some limitations. For example, the sensor's sampling frequency can be adjusted. Only a few producers provide software development kit that allows us to develop our own software and embed it into device. Another factor to consider is that some devices provide signals in real time, while others after the session termination. Yet another factor, some have built-in battery that needs charging every once and then, and some run on replaceable batteries that last for days or even weeks. Let's also remember that the device should be comfortable for the user and preferably also useful. All these factors should be considered in the context of the study we want to perform. We can use less portable devices in the lab study, but we will need wearables for the field study. We revised over 50 off-the-shelf devices in terms of sensors and data availability. The best wearables for emotion, stress and sleep research are Empatica E4 and Microsoft Band 2. Surprisingly, both are pretty old. In fact, Empatica will be replaced with the Embrace Plus model in the coming weeks, and the Microsoft Band is no longer supported. For meditation, EEG headbands are the best choice. One is Muse 2. Recently, producer also deployed a new version called Muse S. And the second one is Dream. It is intended for sleep studies, but in our opinion, it's not very comfortable. Oura Ring is more suitable for undisturbed sleep analysis. The smartwatches like this, by Apple, Fossil, Garmin and Samsung, have proper sensors and provide the best data for activity analysis. As you can see, there is no single device that is the best for all domains that we consider. Producers design devices for specific market needs and use sensors and electronic units of different quality. For example, the average over 5 minutes PPI and heart rate in Oura Ring is insufficient for accurate emotion recognition, but is acceptable for approximate stress detection. And with additional sleep-related data, Oura Ring is actually very good for sleep analysis. The same refers to Apple Watch 5, that provides heart rate data every 5 seconds. This is too rare for emotion recognition, but good enough for activity studies. Here are the devices that fulfill our criteria the best. All of them are portable and quite small. Of course, the portability and size is subjective. 20 years ago, a personal computer was considered portable and small. Today, portables have to be wearable and handy. Perhaps in 5 years, portable would mean barely visible or even implanted. In our study, focused on the affect recognition, we have decided to use a few Empatica E4 devices and dozens of Samsung watches. Empatica offers the greatest number of sensors among the devices available on the market, but is also a few times more expensive than smartwatches. On the other hand, Samsung Watch lacks only the EDA and skin temperature sensors, but offers some other data and allows us to build custom watch applications. Now let's move to the well-off system idea. We are preparing to conduct study on emotion recognition in everyday life scenario. Collecting emotion-related data in the field is a very challenging task. Just imagine that you are driving the car and you have just avoided the accident. Would you be thinking at that moment about reporting your condition? Of course not. You would be shocked, very aroused, stressed. And filling out questionnaires is the last thing you would think of. Our solution to this problem is a pre-trained binary model detecting if you are experiencing an emotion. If you do, it will mark the point and leave you a notification to which you can respond later. So the first phase of the well-off system is about creating this binary model. The second phase uses the binary model to collect signals annotated with rich emotions. The output of the second phase is another model, but this time recognizing multiple emotions. Finally, the last stage is application to the selected domain, where we actually support well-being. At the moment, we don't have any specific target group, but we are collaborating with the nephrologists, and patients with a chronic kidney disease are the potential group for this study. Currently, we are still at the first phase of the system, collecting more data for better binary model. We have 11 participants, 6 females and 5 males, aged 23 to 53. To this day, we have recorded over 6,000 hours for each physiological and behavioral signal. We have gathered about 500 affective samples, neutral and emotional states. One of them is presented in the picture just below me. The participant's baby was choking. You can see the peak in the EDA signal, which is a typical body response to the stressful situation. For each sample like that, we take 60 seconds of signals before the emotional event happened. We then apply the signal processing, like winsorization, Butterworth low-pass filter, and min-max normalization. And using a couple of Python libraries, we extract over 100 features from the signals. After feature selection and reduction, the binary classification is performed. Currently, the best model is combination of tree-based models wrapped with the AdaBoost ensemble algorithm. It has slightly over 90% of F-measure accuracy. We believe that collecting more data will improve this result. We need much more data to apply deep learning techniques anyway. But we also experiment with the sliding window approach to produce more training data. To sum up, consumer wearables are yet to match the medical level devices in terms of sensor and signal quality. The main advantage of wearables is their portability, ubiquity, and multiple sensors enabling large-scale studies in everyday life. To improve data collection in the field, we should first create a pre-trained binary model. The initial results suggest that we can benefit from the use of wearables in well-being support. We found a suitable wearable for each of the considered research tasks. The most important factors to consider when selecting the device for studies is the availability of the relevant and rich data in a raw format. If you are interested in the affective computing, especially in the affect recognition problem, we invite you to visit our web platform. You can find there many resources such as data, tools, models, and references to valuable studies. I'd like to thank the team that is working on this project. We have people from various domains such as machine learning, signal processing, psychology, and medicine. I believe we complement each other very well. Thank you very much for your attention, and please feel free to ask any questions.
Hello everyone, I am Aditya Madhusudanan. I am doing my undergraduate degree in the Department of Electrical and Electronics Engineering at National Institute of Technology, Karnataka. And right now I'll be talking about my work, which is machine learning approach to manage adaptive push notifications for improving user experience. I would also like to thank the organizers of EAI for providing me this opportunity for presenting my paper. Speaking of the contents of my presentation, I'll be mainly speaking about the introduction, background related work, dataset, predicting adaptive notifications, the method that we use, results, conclusion, and future scope. In this modern world, phones are being used extensively, and with the number of apps being installed being very high, each user receives an overwhelming amount of notifications. So our work mainly aims at managing these notifications and generating notifications that are personalized for each user. Since the main aim of our work is to generate personalized notifications, there are no ground truth labels for the notifications as such. Hence, traditional performance measures like accuracy cannot be used. So in this work, we have used measures like click-through rate score, diversity score, and enticement score, which I'll be talking about very soon. Background and related work. A significant amount of research has been done in the field of efficient notification management. And one of the major challenges faced in this field of research is the lack of open source data due to ethical reasons. Hence, synthetic data sets are widely used for training models and for other purposes. So, in one of the research works, the context was based on the IoT devices connected to a particular device at a particular instant of time, and then basically based on these context values, the particular notification or the personalized notifications are generated, and then the IoT device in which it should be shown is also predicted. Another research deals with the usage of machine learning models to predict the time at which a particular notification has to be shown, so that a particular notification which is not relevant at a particular time is shown at a different time. So in our work, the dataset that we have used is provided by the Evaluate Shared Task Challenge 2020. The dataset again that we have used is a synthetic dataset which consists of about 913 notifications and its corresponding context values. So this dataset was generated using a generative adversarial network with gradient penalty. It was actually derived from over 30,000 notifications from about 4,940 smartphone usage logs. Here the whole dataset has about three subsets, which is notifications, context, and engagements. The context basically is used as a feature set for training the model. Notifications is the output label, and the engagement specifies how the user responded to a particular notification. We have also used an OpenAI environment called GymPush, which is used for both obtaining the dataset as well as for evaluation purposes. The OpenAI Gym environment consists of a reinforcement learning agent which acts as a user and then basically responds to a particular notifications and then passes back the engagement value and other performance measures. So here you can see the different features of the context subset and the notification subset of the dataset. Comparing both, you can find that the number of feature sets of the notification subset is greater than the number of features of the context subset, which is one of the reasons of developing a hierarchical model, which I'll be talking about very soon. Regarding performance measures, conventional measures like accuracy cannot be used in our case because we are aiming at personalized notifications, and hence ground truth labels for notifications are not available. So we are using other methods performance measures like click-through rate score, diversity score and enticement score. So the click-through rate score basically shows how engaging the notifications were to a particular user. So we want the CTR score to be high as we want the notifications to be more relevant. Diversity score, as the name suggests, shows how diverse the predicted notifications were, and hence a higher value of diversity score is optimal. And the enticement score is basically a kind of a sanity metric which ensures that the users are not exploited for increasing a higher value of CTR score. Hence, the optimal value of enticement score is neutral. And also, all these performance measures were done by passing it to the GimAI environment that I talked about in the earlier slide. So the predicted notifications are passed on to the environment, and the environment has a narrow agent which acts as a user, and the values of these measures are returned based on the engagement of this user with the notifications. Since our work mainly aims at showing what notifications to show from a given set of notifications, our task is mainly classification. Many of the features in the dataset were categorical variables and hence were encoded using ordinal encoding. Now, models like random forest classifier and tree classifier were trained using this data as a whole. But later we found that the dataset had a lot of repetitions, and also the fact that the number of features in the notification subset were greater than the number of features in the context subset. Hence, we thought of implementing a kind of hierarchical algorithm using tree classifiers. In a custom hierarchical model, basically the dataset is split into different subsets based on the number of unique values that they have, and multiple classifiers, in this case decision trees, were trained so that the output of a particular context, that is the notification for a particular context, will be obtained after joining the output from these individual classifiers. So here I'll be explaining how the hierarchical model works. As given in the flowchart in the slide, notification dataset is divided into three subsets: subset 1, subset 2 and subset 3 for convenience. Now the subset 1 contains the highest number of repetitions, that is the lowest number of unique values, and subset 3 contains the highest number of unique values in them. Now the subset 1 and the concatenated dataset is used to train the classifier, here the tree number 1, such that context dataset is given as the input features and the subset 1 as the output label. Now the subset 1 and the context dataset is joined together to produce concatenated dataset 1 as given in the figure. Now this concatenated dataset 1 is given as the input features for the classifier 2 and the subset 2 being the output label. Now the subset 2 is joined with the concatenated dataset 1 to produce the concatenated dataset 2, which is given as the input features for the classifier number 3 and where the output feature being subset 3. Hence, for a given set of context values, the classifier 1 predicts the visibility, enticement and sentiment, which is then combined with the context values to be given as the input for the classifier number 2. The classifier number 2 then predicts category, LED, RGB, priority, vibrate. These predicted values are then combined with the input of the classifier number 2 to be given as the input of the classifier number 3. Now, the classifier number 3 predicts the app package and subject, and all these predicted values are then concatenated to be given as the final predicted notification set for the given context set. For the evaluation of the models, Gym push environment is used. The Gym push environment for testing gives a set of context values which are then used for predicting the corresponding notification values. Now these notification values are then passed on to the Gym push environment, which evaluates the models and then gives the CTR score, enticement score and diversity score for the predicted set of notification. Given in the figure are the different values obtained for the custom hierarchical model. You can also see the variation of the enticement score with given in this slide is a comparison between the different models that we have trained using the data based upon the measures that we have used. From the table, it can be understood that the proposed hierarchical model achieves the most neutral value of enticement score, which means that the proposed model exploits the user the least amount when compared with other models. Now, the proposed model also outperforms the random forest classifier when it comes to diversity score and click-through rate, and random forest classifier when it comes to click-through rate score. So it can be seen that the proposed hierarchical model in general performs way better than other conventional models like random forest classifier and tree classifiers. Speaking of future scope, neural networks could be trained using the synthetic data that we have used. Also, deep learning models could be trained and compared with our proposed hierarchical model. Researchers in this same field of research could use the performance measures that we have used and also the Gym push environment for comparing and benchmarking their models. That's all. Thank you for listening.